Are you ready?
Yeah. So, I would like to thank you, the organizers of this conference, for the invitation. And I would like to thank the students for their support. They came yesterday to the airport and they gave me some devices I needed to get power in my computer. Now, this is the topic I'm gonna talk about, my presentation. And my background is in engineering, okay? I have an interest in cognition and a long war in it. And I also have an interest in mathematics, but I am a bottom-up mathematician. I see problems, I think I see problems, and I try to describe them in mathematics and find solutions in mathematics. So this is going to be, this is the eye of another. So this is the outline of my presentation, motivation, a chronicle to see how these things evolved, then the theory itself or the approach itself, and then the conclusion. Now, in my opinion, in artificial intelligence, there's a need for a paradigm shift. Now, currently, artificial intelligence is pursued by in these three different directions: deep learning, traditional machine learning, and symbolic AI. Now, this is the hot topic of today. This is a data center. You see a room with lots of computers, and many governments around the planet, some governments around the planet, they spend hundreds of billions. It's not only the United States, it's also Europe. Or they're willing to spend to develop things like that. Now, I took a look at some financial reports by Goldman Sachs, and they estimate that currently 14% of the power, electric power, goes to application of AI today. And this percentage will rise and it will double very soon, in 2 or 3 years. Now, these three approaches to artificial intelligence, they have advantages and disadvantages, are unique in some application domains, but not in all of them. And here is a sketch, okay? Image and speech processing, deep learning is good. And you can read the other ones. Now, when we say deep learning, basically, we mean two things: image, convolutional neural networks, and language, LLMs. And ChatGPT, DeepSeek, and all these things, Gemini, the way I see it, they're algorithms, they're architectures. What lays inside, underneath, is deep learning. Deep learning. Many people who do or are engaged in applications of deep learning, they develop algorithms. Nobody touches the heart. The heart is the models implemented in data centers. That's what we do. We touch the heart, and I will show you how. Now, this is a comparison between deep learning, this column, and traditional machine learning, and symbolic. The red color is the disadvantages, and the green color are the advantages, and the black color letters are in between. Now, our objective is to unify the three. deep learning, traditional machine learning, symbolic AI. In order, why we want to do this modification? To combine the benefits and overcome the drawbacks. And this is what we call lattice computing paradigm. Here, I enter my second chapter, a chronicle, a history, short, of how modeling, why modeling is important, and how modeling was evolved. Now, this slide here is extremely dense. The way I see it, modeling was initiated by Isaac Newton in England. He developed models of the physical world, the motion of the planets, the gravity forces. This was not obvious. There were centuries of thinking before that. And the story, in my opinion, goes back to a Greek philosopher. His name is Pythagoras. And he claimed that the numbers, rational numbers, was the ultimate reality. So the numbers explain the physical world. And these models are based on measurements. That's how real numbers emerge. If you want to measure the length of this door here, you have to define a unit and see how many times it fits. And then there's going to be a residue. You cut it into 10 pieces and see how many times its 10th fits. And that's how real numbers emerge. So Isaac Newton did what he did in the 17th century. He wrote in Latin. Okay. Now, Newton's modeling paradigm worked well for centuries. It was used in physical sciences, that's the par excellence domain, by many scientists, Maxwell, Einstein, even in other disciplines, other domains, like the economy, physiology, medicine, psychology, and many others. The most recent successful example of this type of this mindset are the deep learning models. These are statistical models, neural computing models. They process numbers. And the way I see it, their good performance, remarkable performance, is not due to their computing, but their speed and their capacity, the huge memory. When I was doing my PhD, we were using 3-layer neural networks. Now they're using 40, 50, 60, 70. And we had a few hundreds of links of parameters. Right now they have many more. So this is the publication by LeCun, Bengio, and Hinton that describes the principles of deep learning. So to the students, this is a good reference to read, if you don't know it, of course. Now, I wanted to trace modeling back and farther back and very back. So Newton was not the first. Well, he was the first in recent years, but a critical moment, a critical event happened with a French, Descartes. We are talking about Cartesian system of coordinates. So what Descartes did at that time, he combined Greek geometry, a very successful paradigm, with Arab algebra, another successful paradigm. And if you go back, Greek geometry is based to work done by the Egyptians. And Arab algebra was based, not conscious scientific work, but work done by Sumerians. in these years, 3000 BC. Now, both the Egyptians and the Sumerians developed what they developed because of practical everyday needs. The Egyptians lived by cultivating Nile. So Nile was flooding twice a year, I think, by floods in deep Africa, Kenya, Tanzania. The water and with mud was coming. They were flooding. The Nile was flooding everything, and that made their fields fertilized. But they were losing the marks of their property. So there was a need to divide the space, the field. That's how the first principles of geometry developed. Pythagoras developed the theorem, the Pythagorean theorem, in the year around 500 BC. But to the Egyptians, it was known 1,000 or 2,000 years before. Pythagoras proved it using logic. That's his contribution. Now, the Sumerians, they were people living in today's Iraq between Mesopotamia, between the rivers Tigris and Euphrates, and they need to direct water to water their plants. And they were developing methods that today we are calling them algebra in order to control the time and the quantity of the water. So what I want to say with all these stories is that the Euclidean space is battle tested. It has roots 3,000 or 4,000 years ago to serve practical needs, surviving needs of humans. This knowledge passed from one culture to the other, from one generation to the other, from one continent to the other. So the Euclidean space is very, very well tested. That's my point. Now, in recent years, though, with Industry 3 starting, humans are involved in the modeling. People, especially in the United States and elsewhere, they wanted to automate things. So they wanted to automate decision-making, reasoning. Why? Because when humans are involved, then numbers, real numbers are not enough. Real numbers is a dominant instrument if you study and if you want to interact and control the physical world. But when humans are involved, then other data emerge, like degrees of truth of propositions, true, false, Aristotle logic, structures, like decision trees, symbols, of course. Symbols do not appear in the physical world, they appear in the head of the humans. So these are other types of data beyond numbers. So people started studying, and George Boole developed what we call today Boolean algebra. That's another modeling paradigm beyond the Euclidean space. And today, this is the main instrument in the Silicon Valley to design computers. They do not use the Euclidean space, they use Boolean logic. Now, the study of Boolean algebra led to a notion, theory, which is called lattice theory. This is the theory of order, partial order. And the big name who unified and compiled this lattice theory is Garrett Birkhoff. Okay? He was a professor in Harvard at that time. Now, it is remarkable that this lattice theory gave way and introduced somehow or helped understand probability theory. What is remarkable here, and I want to point out, is that the Euclidean space is not anymore a monopoly, even in the physical world, because in 1954, the Nobel Prize was given to Max Born, and he used probability theory to describe quanta, the behavior in nature. And this probability theory has been formalized by another Russian mathematician called Mogorov in 1933. And Birkhoff showed that this probability space is a mathematical lattice. So in my opinion, mathematical lattices is probably the new instrument to unify the different approaches in artificial intelligence, because it combines the Euclidean space. This is an example, a specific one of a lattice theory. It combines probability theory and other things. Now, me, with my team and other collaborators during the year, we have introduced what we call lattice computing. That means you have a mathematical lattice and do computations in it. About 20 years ago, I published a book here, 2007, and then I published another, there was another book, Ritter and Ursid. Ritter is the professor, he's retired now in Florida. Ursid is a Mexican, he's from Puebla. And I have a book also with Ritter, but I don't, yeah, it's here. Yeah, there's another book, but well, I don't mention everything. And this is an edited journal I made where I present this lattice computing principle. Now, the new thing is that in lattice theory, if you develop methods in lattice theory, then you can compute with semantics. That's the new thing. And semantics are represented in this approach by partial order. That's semantics. Simple things. Partial order means semantics. Simple things, not complicated. Now, I will show some unification of different mathematical, different data. Now, the first data domain, of course, are the real numbers. The set of real numbers is this line. This is a totally ordered lattice. If you have two numbers, one is smaller, the other is bigger. This is total order. If you have the power set, this is a Boolean lattice. Okay, you know that from Boolean algebra. Here you do not have a total order because you may have two elements. AB is smaller than ABC, but if you have this set and this set, none is bigger than the other. These are parallel. This is an example of partial order. Now, this is another example of a lattice. This is a tree, decision tree. Okay? And decision trees exist in human language and other structures. So this is our proposal. Compute with semantics by doing calculations in lattices. Now, I show some instruments in this domain for reasoning, because lattice theory developed initially by George Boole and De Morgan. One was English, the other was Scottish, both were British, regarding logic. But I introduce also a real function I call valuation. It has these properties. These are very simple things. They look complicated, but they're very simple. and a fuzzy order function that has to satisfy these two conditions. In any algorithm that uses this function, I call it fuzzy lattice reasoning, FLR. I show two specific functions. These two functions emerged from a work by Stephen Grossberg. I did my PhD in the United States 33 years ago, and I was working on Stephen Grossberg. And I took two functions, he called them, with his wife Gail Carpenter, they call them vigilance parameter and choice Weber function, and I unified them both, and I extended from the Euclidean space to a lattice domain, and I call it fuzzy order. And I describe everything in this publication. My presentation will be available to the people who have to collect it, okay? Now, with an ordered function, sigma, you can carry out four types of reasoning. Inductive reasoning. Inductive reasoning is to go from the specific to the general. The other is deductive reasoning, to go from the general to the specific. The other is reasoning by analogy. If it looks like it, do something similar. And then it's abductive reasoning. That is not only to give the decision, but also to give the explanation, the rules. This is very important, missing in deep learning. Some popular practices that fall into this LC paradigm. One is a conventional fuzzy inference system. The way they decide the degree of activation of each rule is achieved by an underlying inclusion measure. That's my discovery, and nobody has noticed it. But it fits in the theory. Another thing is that the base rule is used for the last 2 or 3 centuries. Base rule is one example of an order measure. It fits perfectly inside this framework. Now, a positive valuation function, it's a real function defined on a lattice, is one way of introducing nonlinearities, one way of distorting the space. It's called, a space that is distorted is called Riemann space, after a German mathematician of the 19th century. Now, some advantages of lattice computing. The first is hierarchical fusion of numerical and non-numerical data. This is called also modalities. You can fuse modalities, sound, vision, and so on. Rigorous mathematical analysis and design, decision support based on logic, computing with semantics. Now, the most successful lattice, we have done a lot of work, and I will say several things about it, the lattice of intervals numbers. That's what we will talk about. Now, this is an example of an intervals number. Okay, intervals number is, looks like a fuzzy set, a fuzzy number. But it can be represented in 2 different but equivalent manners. One is by a membership function, the other is by alpha cuts, intervals. We have done that in this publication, okay, about 15 years ago. Now, this representation is good for interpretations, for explanations. This is good for computation. And I will explain why. Now, another thing you can represent with an intervals number is a probability distribution function. In this case, this is a cumulative probability distribution, and you have the 2 equivalent representations, membership function and interval representation. And this is the paper where we presented an algorithm for doing so. Now, I will introduce a Hilbert space. Hilbert was a German mathematician, the best, as far as I know. What he did is this. He studied the Euclidean space, which was studied for thousands of years, and he made an abstraction. He found all these elements from the Euclidean space that matter, that are important. The definition of a Hilbert space includes three parts. The first part is this space set has to be a linear space, vector space. Vector space has to satisfy 8 conditions, specific ones. I do not show them here. They are known. Okay, you can find them. First. Second, there has to be an inner product. This is an operation between vectors, which in terms of the Euclidean space can define the length of vectors and also the angle. If you have two vectors, the angle, can measure the angle. Now, the third property is due to a French mathematician, Auguste Cauchy. A Cauchy sequence looks very mathematical, but is extremely practical. Our interest in that is that if you train a neural network and if it behaves the output as a Cauchy sequence, that means the output gets smaller and smaller and smaller and smaller. You stop training because it will converge. So to know that this linear space with an inner product has this property, every Cauchy sequence converges, gives us a hint for convergence, a guide for convergence. Now, since the Hilbert space is an abstraction of the battle-tested Euclidean space, and if we can show a Hilbert space that can accommodate semantics in terms of partial order, then this is a very promising domain to do calculations. Go back to the real number again. The line of real numbers is totally ordered. If you take two elements, two numbers I mean, one is larger, the other is smaller. Total order. If you take the intervals of real numbers, these are partially ordered. One may be smaller or bigger than the other, or they might be partially overlapped or not overlapped at all. That means parallel. Now, you take, now it's a little bit complicated, but these are extremely simple notions. If you take this Cartesian product, and if you take this order, the first and the second, the end of the intervals, this is called lattice of generalized intervals. Now, in this lattice, it is a lattice, you define two operations, addition, that's simply, and multiplication by a real number, that's simply. Now, the difference to end up with a Hilbert space is here. I know mathematicians, trained mathematicians, applied mathematics, that they use this operation. If you multiply 2 times this interval, 1.2, the result is 2.4. Okay. But these mathematicians, which multiply negative number with a regular interval, then they say this is not defined. The critical thing, the critical decision I told you that I defined it. The result is this interval, which is not a regular interval, because this one here, the first, is bigger than the other one, but I accepted it. That's why I call it generalized interval, because it's not a regular interval. And this critical decision here will lead me to a Hilbert space. So it turns out that this Cartesian product generalized intervals is a vector space. I don't want to go through all this mathematics. I will show you a result. Then I define a generalized interval number by mapping each number in this interval to a generalized interval. And in this lattice, I define addition and multiplication like that, and I've proven that this space G is a linear vector space. In this space, then, I define this operation, and I show that this is an inner product. It is an inner product because these two functions are integrable in the sense of Lebesgue. Lebesgue is another French mathematician, and he has shown that L2 functions, product of two functions, is integrable, and it has an inner product. Finally, this space G is a Hilbert space. Okay? It has these three properties. Now I have defined it more than 15 years ago, the interval number formally by this action here. That shows that an in is a gene. So a gene, generalized interval number, is something more general. But the in is more useful because it can represent fuzzy numbers and probability distribution and real numbers as an extremely special case. Now, what I do here is I define this function, a similarity cosine between intervals of int. You know, when deep learning operates in the background, they use similarity functions to define how similar are two vectors of numbers. In these vectors of numbers, they represent concepts. So what I have now is the machinery, a space that includes the Euclidean space as a very, very, very small subset of it. And it has the structure of a Hilbert space. If you see and you think what neural computing does the operations of a Hilbert space. The so-called dot product that is the input to a neuron, what is it? This is an inner product. And then you have the addition, and it goes through non-linearity, and you do this thing over and over again. So now I keep these properties, these operations, but in a larger space. Okay, that's the idea. Now I show here, this is kind of example, the next 1 or 2 or 3 slides. I show here an in computed by samples with 2 different interpretations. This is the probability distribution, and this is a fuzzy set. So from a set of numbers, you can calculate a distribution. This set of numbers would be a very big set, and it can be represented only by a finite number of levels. So you may have big data here, meteorological data or medical data, huge numbers, and you may represent them with a small number of real numbers to any degree of accuracy. So you have a representation of all order statistics by finite number of numbers. Now this is something very new. If you have 2 real numbers, on the real line, their inner product is either 1 or -1. The angle between them is either 0 or 180 degrees. Okay? Now, the magic with these things is that you may have intervals numbers that are orthogonal. So what I did here, this is an example, okay, demo. I kept this one still, not moving, and I started moving. This is a trivial interval number. It's a number. I started moving it to the left and to the right along the whole line of real numbers. And at each point, each location, I was computing the angle, the similarity cosine. And I saw that for negative values, it was -1. And for positive values, it was +1. So either +1 or -1. But if this in, the moving in, was not trivial, then as it approaches this still in, the cosine is starting taking value from -1 to +1 continuously. So at a certain point, these two interval numbers become orthogonal. Now this space is linear, but we can introduce non-linearity. And I'll show how. It's very simple. We have a function. You apply this function. You apply this function on a vector, and you got the mapping of this function by calculating the map fixed value of the interval. Okay, that's how you can. If the function is strictly increasing, then an interval is mapped to an interval, smaller, bigger. Okay, and if we have a name, that's the example. If we have these three ints here, f1, f2, and f3. If you pass them through this logistic function, then the output will be 3 ints again, but distorted. So this is what we need as an activation function to the new type of neural networks. This is nonlinearity that does not distort the in. You have to be in. Now, the magic thing is this, that in our neural network, in nonlinearity can be introduced as a neuron activation function, as usual, but also as a link weight. The weights in conventional deep learning neural networks are numbers. That's it. In my case, they're functions. And there is an extremely interesting benefit practical in it. Reducing the power dissipation. The problem that Americans and Europeans have is heat, power consumption, water to cool it. By putting more parameters in the weights, you may have a total number of equal parameters, but half the number of neurons, half the number of the architecture. That's the point. Now, this is the architecture. It's a neural network. The inputs are ins. You have the biases and everything. The difference is that you may have weights on the links. The weights of the links are increasing functions. They're not, you see, a number is a special case of a function. For example, if you have the weight of 2, it's like having the function 2x's. So the input is multiplied by 2 and you produce the output. So in our case, you have a strictly increasing function, but you can also have a strictly decreasing function. Then you have to flip it somehow. So it's a stronger possibility. So this is the model of a neuron, okay? You have the summation here, you have the inputs are ins, and the weights are increasing functions, and you have the bias there, and you have the nonlinear activation function, and you produce the output. What are the key drawbacks of data centers today? High energy consumption, carbon footprint, cooling, heat management, and blah, blah, blah. They all have to do with the size of the architecture. Now, all these big guys, big tech companies, they have developed some ways of tackling the drawbacks. Basically, they do not touch the model. They do a management system, an algorithm, an intelligent algorithm, but they do not touch the heart. We touched the heart. That's the difference. For good or for bad. Okay. The number of tunable parameters, these are the weights of a neural network, are in the order of hundreds of billion. This is a tremendous big number. But I know from this publication, it's already old, 4 years old. Now, typically, there is one parameter between two neurons, not any two neurons, because not any two neurons are connected, but those who are connected, they offer one parameter to this set of hundreds of billions of parameters. In our case, we introduce more parameters between two neurons. So, what neural networks do is a function approximation problem with many parameters. I have an instrument to keep the same number of parameters, but with a much smaller architecture, because I introduce parameters on the link between two neurons. So if I increase the number of parameters this way, I may be able, I don't know, to decrease the number of neurons. And if I half it, then I may need half of the power, half of the water. I'm talking about big numbers, half of the money. So instead of 200 billion, I may need 100 billion. Probably, I don't know. Now, my interest and my team, we are interested in intelligent robots. And robots are driven by software. Software drives robots. The software, what it does is that it implements a model. The typical model is developed in the Euclidean space. We want to go to this space, LC space, in order to design machines in the winner sense, okay? Cybernetic sense. That's our vision. Now, 3 selected publications. This is the book I wrote about 19 years ago. And then I have this editing book. Now, in my publication in this conference, I present some of the mathematical results, not all of them, but I present no proofs. The proofs have been developed in this publication. I send it to a book couple of days before I get the plane to come here. Okay, about a week ago, last week. So I will see if the proofs are correct. I think they're correct, but we will see. That's it. Thank you.
Thank you so much, Professor, for your wonderful presentation, and thank you for making the long journey to be here with us. And it's truly an honor have you with us. Well, does anyone have questions? Sure.
Very interesting talk. Thank you very much. So I can't say I understood everything, but I do think I understood a good chunk of it. I understand sort of the generalization over some of the typical machinery that we would see in neural networks to this IN, your Hilbert space. One of the things that I was curious about, actually two things, let me say two things I was curious about. One is the learning algorithm that you use. Are you using some kind of a flavor of back propagation that works with intervals? Or is it something different?
This is our most important problem at this point.
Okay.
Because the way we've done it by now is we are using, to find optimal parameter values, we are using a genetic algorithm. The reason is that there is no notion of a derivative. We know which direction to go, but we haven't gone there yet. This is going to be probably one PhD in the following years, and we maybe have common PhDs between Greece and United States or Greece and Mexico, if there is an interest. Thank you.
Okay, great. Yeah. The other question I had is you showed a diagram of the different connectivity between different neurons. I'm not sure what the slide number was for that. If my memory is correct, it doesn't quite, okay, so the arrows going in, those are the bias numbers and you have the weight. So it is kind of a layered architecture in exactly the same way you would imagine for deep. Okay.
The idea is that if this thing is to go far, I don't want, I don't want to destroy the Tower of Babel. I want to keep increasing it, to modify it a little bit. People invested too much time, too much money. You cannot disregard the whole thing. You have, or I want, or I have to somehow complement it or enhance it. So this is not something radically different, but it's new.
Great. Thank you. Appreciate it.
So first, that was amazing. I'd like to talk to you afterwards, but there was two things. So one thing that does fit when you were talking about having functions instead of numbers, like for the weights between two neurons, like so I've been studying LLM, like transformer model inference for optimization purposes. And one of the things that they found that even in the non-MOE, like expert, like kind of models, the dense models are at inference time only a handful. It's like the activations are still very sparse, so there's a lot of waste in these models at inference time, and it's just the nature of the beast. So something like this might actually be able to mitigate some of that, because it feels very strange that you have so many of these weights, but the activations are very sparse, even though the models themselves are dense. Now there's newer models like the MOE models that are trying to get around that, but it still feels like there's something missing. So this totally makes sense. And then the other comment was when you were talking about the lattice-based structures supporting multimodal data possibly, there's literature in neuroscience that actually talks about this. So it's very much tracks. Thank you.
Okay, we have an online question. So, does your theory address learning, like tracking functions that could change over time? Oh, this is a question made by an online attendee. Okay. Does your theory address learning functions that could change over time?
But I think we should develop a derivative in a further version of the delta rule. We are working on that.
Thank you, doctor.
Okay, so let's continue with the next presentation. Thank you so much. Okay. ¿Presenta quién? Ya sé, tranquilo. Okay, our next presentation will be performed by Xin Huang. Xin, are you here? Are you ready?
Yes, yes, I'm here. Yes.
Okay, we can hear you.
I'm going to share my screen now. Okay.
Yes, we can see your slides.
Can you? Oh, no. Yes.
Okay, we can see your screen and hear you clearly. So, are you ready?
I need some question. I need to solve my question. Sorry, wait a minute. Sorry.
Okay, don't worry.
Okay. Okay, I'm okay. I'm okay. Can I begin? I'm okay. Hello?
Hello. Yes, we can hear you and we can see your screen. So go ahead, please.
Okay. I will begin my presentation. Hello everyone. I'm Xin Huang. I'm from Ningbo University, and I'm here to present our work on CogHelp, cognitive architecture for adaptive helping decision in multi-agent emergencies. Okay. This is the outline of my presentation. As urban public safety incidents become increasingly frequent, and the cost of conducting real-world trials for potential dangers remain high. Code simulation in emergencies has become a crucial area of research. The left image shows a real-life evacuation trial, where the right image demonstrates code simulation technology used for crowd evacuation. Next. Okay, next. Uh, Existing crowd simulation studies have incorporated agent perceptions and intentions, developing various cognitive frameworks to give agents human-like cognition. These modules simulate human responses in emergencies, offering realistic portrayals of behavior in emergencies. However, previous studies face two key challenges. The first, current models focus on evacuation, overlooking other behaviors such as helping or observing. Second, they fail to capture the dynamic nature of human behavior, where individuals may shift from evacuation to helping or observing based on the evolving environment. This these two images illustrate a fire scenario. As the event progresses, the crowd's behavior shifts. More pedestrians move toward the fire to help. To address these two issues, we propose CogHelp, a cognitive architecture for adaptive helping decisions in emergencies. It's consisting of four modules: perception, emotion, decision, and behavior. The perception module gathers environment data, including danger and neighboring agents' position and their emotions. The data informs the emotion module, where agents calculate their emotional state with using the ocean personality model and emotion contagion. The decision module integrates inputs from the perception and emotion modules. It's incorporating risk levels, emotions, and social evaluations to calculate payoffs for helping, escaping, or observing behaviors. Finally, the behavior module X calculates the choosing behavior. Our cognitive architecture integrates game theory and the emotional contagion theory. The specific details are described in our paper. Based on the cognitive architecture, we designed agents equipped with 316 auditory and 120 visual perception. The agents make decisions in response to emergencies, such as escaping, observing, or helping. It's according to their cognition of emergencies. So we designed two simulation experiments. In the first experiment, we set up different risk levels in the environment and placed 14 agents in the scenes. The personality traits of the agents were adjusted to be stable, sensitive, and random types to observe the impact of personality and risk levels on the agent's behavior. In the second experiment, the environment was set to a medium risk level, and the agent had random personalities. We observed the trajectory changes of the agents with 16 frames and recorded the number of agents whose behaviors changed every 5 frames. The goal was to verify that agent behavior based on the cog help is dynamic and adaptive. It's changing according to the environmental shifts. As shown in the figure, as risk increases, fewer agents engaging in helping behavior. Crows with a stable personality have the most helping agents, while those with sensitive personalities have the fewest helping agents in the emergencies. The table shows that for stable personality crows, the average number of helping agents per frame in low-risk scenarios is 2.25. It is 6.4 times higher than for sensitive crows. From this table, we can know as risk increases, the number of helping agents decreases. The next experiment, we realized their trajectory changes at 4 time points, 0, 15, 16, and 16 frames. Agents are represented as cylinders, green for calm agents, red for panic agents, and the yellow for those willing to help. The trajectories show that agents first escape, then transition to observing or helping. This chart shows the frequency of behavior switching among 14 agents over 16 frames, with an average of 11.3 agents changing behavior per interval. These two images are screenshot from the first and 15th seconds of a fire video. We recorded the number of bystanders and heroes each second. Then recreated similar scenes with agents to simulate human behaviors by adjusting risk levels and personality parameters. This is a screenshot from our simulation. From the trajectories, we can see that it closely resembles the real video, with many individuals participating in the helping. This figure compares the number of heroes and bystanders in the real and simulated environments over 15 seconds. The overall production accuracy is above 18%. In discussion, we think CogHelp is a cognitive architecture modeling adaptive helping behavior in emergencies, integrating emotion, contagion, and game theory for dynamic human response simulation. Our experiment shows that agents shift behaviors based on changing conditions. Our CogHelp model predicts pedestrian behaviors with over 18% accuracy, aligning well with real-world data from both bystanders and heroes. I'm over this. Thank you for your attention. Do you have any questions?
Thank you for
Hello, I can hear. I can hear.
thank you for your presentation. Does anyone have any questions?
Hello, thank you very much for the presentation. I particularly enjoyed the trajectory diagrams. That's very interesting. One thing I was curious about is in your diagrams, your earlier diagrams, and the one that you showed for the real video with the large percentage of heroes, I was curious, what is it in the environment that is encouraging so many heroes in that later example versus the earlier example where it seemed like a minority of the participants were heroes, many were fleeing or standing still? I'm sorry, were you able to hear me?
Uh,
Did the question make
uh,
sense? I can try to rephrase it if it didn't. So
our cognitive architecture incorporates the basically theories such as emotion, cognitive theory, game theory. Uh, in our scenario, the agents will choose the biggest payoffs. So in the real video, we record the trajectory. Then we compare the trajectory with the real video. We record someone is the hero, someone is the bystanders. Then we have a comparing in our scenery and the real video. In our figure, we record human behavior by 1 second. In our simulation in our simulation, we record the agent by 1 second. Their behavior in we can compare their behavior. Then we can get how many pedestrians to helping, how many pedestrians to observing. Then we our cognitive architecture is based on the emotion emotion serial and the game serial. So the agent is able to choose different behavior. Then they will make their decisions.
Okay. I think that makes sense. So you mentioned payoff. Was the payoff configured differently to encourage heroes in the last example versus the fleeing or bystander behavior?
What?
Oh, it's okay. Don't worry about it. It's okay. I was just trying to compare the two different types of trajectories, but thank you.
Any other questions?
Okay.
I'm sorry. I can hear clearly. I can hear clearly.
No worry. There's no more questions. Okay. Thank you so much, Shin.
Oh, okay.
Well,
I will close my screen. I will
sorry.
close my-
Excuse me. Okay. Well, let's continue with the next talk in the schedule, which will be presented by Jovana Bukmirovic. Jovana, are you ready?
Yes, I'm ready.
Okay. Go ahead, please.
Okay. Can you see my slides?
Yes, we can.
Okay, then I'll start. Hello, everyone. My name is Jovana Bukmirovic, and I'm from the Free University Amsterdam. And today I'm going to talk about our research titled A Fifth-Order Adaptive Network Model of the Role of Epigenetic Modification Caused by Early Life Stressors in Borderline Personality Disorder. First, I'll explain the context and the theoretical background information that served as the basis for the model, and then I'll show the designed model itself and the conducted simulation experiments. So for context, epigenetics play a significant role in mental disorders, and there are complex dynamic and adaptive interactions between the environment, epigenetic modifications, and the development of the disorder. And it's important to investigate and analyze these interactions to potentially improve our understanding and treatment of the disorder. So about the disorder itself, the diagnostic criteria according to the DSM-5 are instability in affect regulation, impulse control, identity, and interpersonal relationships. Besides that, intense emotions and stress seem to be central to other symptoms and coping mechanisms such as substance abuse. And stress-related dissociative experiences are frequently reported in patients with BPD. And there seems to be a strong association between the disorder and child abuse and neglect. So epigenetic processes affect gene expression without changing the DNA sequence itself. And these processes can be influenced by environmental factors. And childhood is one of the susceptibility periods in which epigenetic programming takes place. And something to note, DNA methylation leads to decreased gene expression in most genes. So specifically for borderline personality disorder, research has found an association between increased methylation of the NR3C1 gene, childhood maltreatment, and the development and severity of the disorder. So about this gene, the NR3C1 gene, also known as the GR gene, this gene encodes the glucocorticoid receptor protein. And these GR proteins bind to the stress hormone cortisol, which is produced by the HPA axis. And this acts as negative feedback to the HPA axis. So the HPA axis is the hypothalamic pituitary adrenal axis. Here you can see a figure where there's a schematic representation of this axis. And this axis regulates the neuroendocrine stress response of the body. And so when we talk about these GRs, they are expressed throughout the whole brain, but there are some brain areas with a higher concentration of GRs, such as the PVN, hippocampus, and prefrontal cortex, making these the main inhibitors of the HPA axis. On the other hand, the amygdala serves as the main activator of the HPA axis. So what are the exact effects of this epigenetic change? Well, when this GR gene is hypermethylated, this leads to decreased expression of the gene. And this then also leads to decreased negative feedback to the HPA axis because GRs aren't as available anymore. And this leads to increased cortisol levels. And then prolonged exposure to cortisol can lead to a constant state of hyperarousal of the body, triggering the fight or flight response. And this also leads to abnormal nervous system activity, overstimulation of the amygdala, hippocampus, and the prefrontal cortex, and also to inappropriate behavioral stress responses. And this part of the figure summarizes the possible consequences of overstimulation of these brain regions by cortisol quite well, such as perceiving the environment as a constant threat, unstable and intense emotions, and cognitive dysfunction like the loss of rationality and decision-making capabilities, which are all commonly seen in borderline personality disorder. So for the model, an adaptive temporal causal network modeling approach was used, where you have dynamic states, each with their own network characteristics, namely the connectivity characteristic, where a directed connection indicates a causal relation with weight omega. You also have the aggregation characteristic, where a combination function C specifies how the combined causal impact of incoming connections to a state is calculated. And you have the timing characteristic, where the speed factor eta determines how quickly a state adjusts its value after receiving the aggregated causal impact. And here you can see the equation that is used for the simulations later on that incorporates these network characteristics that were just mentioned, so the eta, C, and omega. And then you have a dynamic model, but to make it adaptive, these network characteristics can be made adaptive by adding self-model states representing these characteristics, which are placed at higher network levels above the base level. For example, self-model states W are used to represent adaptive connection weights omega. This can be done iteratively throughout higher network levels by adding second and higher order self-model states. And this principle is also used in the design model. Then for the simulation experiments later on, two combination functions were used, namely advanced logistic sum and step ones, each with their own parameters as well. So then we get to the design models. So actually 3 models were designed in total, but 2 of those are small extensions of the main model, and they both explore the efficacy of a specific type of therapy. But first we have the main model that incorporates the role of epigenetics in the development of the BPD, which can be seen on this slide. It consists of a base level, which represents the stress regulation, and 5 self-model levels that each represent a biological component such as DNA or proteins. On the base level, the body of the individual perceives a stress stimulus, after which the body prepares itself for a stress response. In a normal situation, the GR state will suppress the stress response by sending negative feedback to the HPA axis state. However, when the epigenetic change takes place on the fifth self-model level as a result of early life stressors, this affects the activation of the GR state on the base level through the adaptive weights and leads to impaired negative feedback and the subsequent development of the disorder. The second model additionally incorporates a hypothetical epigenetic therapy by adding a therapy state to the fifth self-model level. It has been found that trigostatin A can demethylate the GR gene in adult rats, and thus it has been used here in an explorative way to find out what the potential effects could be of a hypothetical epigenetic therapy that demethylates the affected gene. The third and last model incorporates a standard form of therapy, in this case dialectical behavior therapy. This form of therapy works more on a cognitive and affective level and possibly lowers the activity of the amygdala. But when we look at it from an epigenetic perspective, it doesn't directly address the cause of the symptoms. So in contrast to the epigenetic therapy state, the dialectical behavior therapy state is added to the base level. So then we have the simulation experiments. First, we have the simulation experiment for the main model. I'm not sure if all the details are visible, but I'll go through the main points. The x-axis represents time and the y-axis the activation level. The simulation on the left shows all the states, while the one on the right only shows the higher level states, representing the production and availability of GRs. So in the simulation on the left, it can be seen that before the epigenetic change, so until time 150, when only the regular stress stimulus is present, the base level states involved in stress regulation are relatively low, and the suppression by GRs still work as intended, also shown by the higher level states that are still active in the simulation on the right. But between time 150 and 280, the early life stressor is present and the hypermethylation of the GR gene takes place. And after the epigenetic change has taken place, so from time 280 onward, states representing the affected brain regions and the HPA axis cortisol level and nervous system activity are highly active. This represents the hyperarousal of the body and subsequent behavioral stress responses commonly seen in BPD, even when the early life stressor itself is not present anymore. The second simulation is from the model with epigenetic therapy. Between time 400 and 530, the epigenetic therapy takes place, demethylating the GR gene, and thus the GRs become active again. This is also shown by the higher level states going up again in the graph on the right. And after the epigenetic therapy, the activation levels of the affected base level states are comparable to those of a healthy individual. And then the last simulation is from the model with dialectical behavior therapy. Again, the therapy takes place between time 400 and 530. A couple of base level states slightly go down, but the effect doesn't persist when the therapy is over. Because the epigenetic issue isn't addressed, the GRs remain inactive. And this is also shown by the higher level state not going up again in the graph on the right, in contrast to the simulation with epigenetic therapy. So the model successfully described the effects of hypermethylation of the GR gene and two forms of therapy on borderline symptomatology based on the simulation experiments, but there are also some limitations. So the models are a simplification of reality. The disorder is likely caused by multiple genes and not just one. And I'd also like to add to that this current research is a qualitative analysis, but for future research, real-world data should be used to improve the accuracy of the simulations and potentially personalize them to individuals. And the research on the epigenetics of BPD is still in its early stages and has been fairly inconclusive so far, making it difficult to draw general conclusions related to the affected genes. And there's a high rate of comorbidity in patients with BPD, also making it difficult to know whether certain findings are exclusively related to BPD or also to other disorders. Yeah, that's it.
Bueno. Thank you for your presentation, Giovanna. Congratulations. Any questions? Nope.
Okay, there's no questions. So thank you, Giovanna. Let's continue with the next presentation that will be performed by Artemis Hajiloizou. Artemis, are you ready? Artemis?
I can't hear anything. I don't know.
Yes, you can unshare your screen. Thank you. Giovanna, can you hear me?
Yeah. Yes.
Okay. Thank you so much. You can unshare your screen.
Okay. Yes.
Thank you. Artemis, are you ready?
Hello, yes, I'm ready. Would I be able to share my screen and show my e-poster?
Yes, please.
Of course. Can you see the poster?
Of course. Go ahead, please.
Of course. Hello, and thank you for attending. My name is Artemis Hajiloizou, and I'm presenting joint work with Jan Scher and Peter Rolfsma from the Rijksuniversiteit Amsterdam and the Hague University of Applied Sciences. Our project is titled Using AI Coaching to Improve Cybersecurity Decision Making, an adaptive network model to analyze AI-supported government surveillance, trust, and threat identification. We ask a simple but urgent question. Can AI coaching improve threat detection, decision consistency in government surveillance, especially when human decision makers are prone to stress, information overload, and most importantly, take into consideration public sentiment shifts? We live in an era where over 1 million cyber attacks occur daily, and trust in government surveillance is declining. While traditional cybersecurity models focus on technical threats, they often ignore cognitive and emotional dynamics. Previous work have a lack of capturing how public sentiment affects these decisions. Therefore, our project and our work addresses this gap by modeling the mental processes of our surveillance employee with and without an AI support. The scenario that was created for this project is that an employee in a government surveillance agency monitors threat intelligence, considers public response, and makes decisions on how and when to intervene. 2 models were built. One, a human-only model, where decision quality can degrade under pressure, stress, mistakes, etc. And a second model, an AI coach model, where the AI only intervenes when the employee diverges from ideal reasoning. These 2 models can be seen under the methods section in the poster. And now I would like to explain a little bit about the approach and the methods used in this project. So each model includes 3 layers. The base level layer, which is the pink plane, and this captures the basic scenario. The second level, which is the first order learning level, which captures how decisions improve over time. And the third level, which is the second ordering level and shows how quickly the learning happens. In each model, X represents each factor of the scenario, and a network model is a summary of these factors. The W states that can be seen in the second level represent the connecting strengths between 2 cognitive states. And the HW states that can be seen in the third level control how fast these W states adapt. However, in the second model, there is the addition of monitor states and WWW states to allow context-sensitive AI interventions without overriding human agency. This was a really important addition to the second model to make sure that the AI coach only intervenes when the employee makes not the correct decision according to the AI, that it doesn't always override the decisions of the employee. In the results section of the poster, these were conducted using MATLAB, and the two simulations show each simulation captures the different model. By comparing these two simulations to each other, we were able to make the following conclusions. That the AI coach model produced more stable and accurate decisions across time. Public feedback, which was the state X8, was more precisely estimated, and threat detection, which was the state X7, improved even under imperfect learning weights. Importantly, AI never replaced the human. It supported decisions selectively. For the analysis of this project, 2 what-if analyses were conducted, and a risk assessment was also conducted to quantify decision quality. From these results, it was easy to conclude that the human-only model showed irregular performance when public opinion was weak, and the AI coach model performed robustly across a wide range of scenarios, showing higher impact scores. But these scores reflect successful outcomes, not risk. So for the tables I added in the analysis section of this poster, it might seem that there's a higher number for the AI coach showing more risk, but that higher number shows actually a higher successful outcome for the AI coach model. The key insight of this project is that AI assistance improves both performance and legitimacy, but only when designed to preserve human agency. Rather than replacing humans, AI can act as a corrective lens, amplifying good decisions. To conclude, AI coaching enhances decision-making in cybersecurity monitoring. It maintains accountability and could build public trust if used ethically. Thank you so much for your time, and I'm open to discuss some of the feedback I received from the reviewers on the project as well now.
Thank you for that poster presentation. Does anyone have any questions? Oh.
Okay. Artemis, thank you so much for your presentation and congratulations.
Thank you so much.
Well, let's continue with the presentation that will be performed one more time by the keynote speaker, Vasilis Kabourlassos. Hello.
So this is going to be an application of what we said previously. So we will show a specific example application. The application domain is robot vision. So here I will present a CNN type network using the new mathematical instruments. The problem is important. I'm involved with agricultural robots. My motivation is this. Every human on the planet wants to eat, but nobody wants to produce food. I know that. I have traveled quite a lot along the planet. They have this problem everywhere. I know they have it in the United States and in Europe. They have it in China. They have it in Africa, everywhere. So the idea is to develop robots that they do agricultural jobs and not only surveillance or spraying, but also doing manual jobs. The first job of importance is harvesting. There are many others though. To have this thing, you have to have vision. And this is the topic of this small application. This is the outline. Several of the things I will say I have already talked about before, that the popular models, they ignore semantics. So what we want to do here is to show that we can compute with semantics. I mentioned about Newton modeling in the Euclidean space. This modeling worked well for centuries. Now lately, deep learning became very popular. And deep learning, usually, typically, they have two types of mainstream applications: vision and language, CNNs and LLMs. Okay, this is the famous paper that was published 10 years ago. Now, when modeling involves humans, Newton developed his models for the physical world. And the physical world does not include humans. It includes nature. And to create a representation of the physical world, you measure. And from the measurements, you create a representation of the physical world. And then within this space of measurements, that's the Euclidean space, you develop models and you do all things. What I say sometimes joking is that engineers cannot escape Pythagoras. They are framed within Pythagoras. George Bull was the first who escaped the cave, I think. Now, the same story, modeling in logic was the first attempt to go beyond the Euclidean space. And I will repeat part of the mathematics, but I have some new results also at the end of this presentation. This is the LC paradigm. I talked before, logic, reasoning, okay. Intervals numbers, I said these things before. I don't want to repeat them. Hilbert space, the properties. Okay, I don't want to repeat them again. The inner product. The similarity cosine. Okay, and these two interpretations. Two basic interpretations, like a probability distribution, like a possibility distribution, computed from numerical samples. And the network architecture, the same as before. Now this thing is new, okay? What I want to do here is to detect the presence of grapes. So what we want to do is to harvest grapes. And I will focus on the vision, robot vision part of the whole project, okay? Now I want to detect grapes from non-grapes. And if there are grapes, then I do a series of actions to harvest them. So this is a true positive example, and this is a false positive. Sometimes it gives me a bounding box, but there's no grape in it. So I want to disregard, to ignore these images. The robot proceeds alone. We have done experiments in northern Greece, so we have a feeling about this application. What we did as a first place is that we used an RGB signal from the image, RGB, red, green, blue. And for each image, we calculated an in. Each pixel on an image has 3 components, RGB, intensity levels. So for each channel, 3 channels, RGB, for each channel, there is a distribution of intensity levels. For the first one, for the red, we calculated an in corresponding to the red channel, the green channel, and the blue channel. This first line corresponds to the presence of grapes, when grapes there are in an image. This triad corresponds to non-grapes. Okay, it might be leaves, sky, earth, fences, but no grapes, or not many grapes. So I want to take action for this type of ins, but I want to ignore and take no action for this 3 ins. Okay? Now, we developed an algorithm that partially answers the question of Shen, the previous, regarding what kind of algorithm we used in order to do the optimization of the network. So this is an exhaustive search with a genetic algorithm. Very elementary things, because the network is very, very small. We can afford it. If the network grows big, forget it. You cannot do these things. And here we use 2 different indices to decide. The upper half of the table corresponds to distances between ins. No, the upper part is similarity cosines between ins, and the lower half are distances. Okay, using specific equations, we were playing here to define to find out what is more effective, similarity cosine or distances. Okay, and here is the result. We used in this simple experiment, we used only 120 images. In the new paper, we are working for the journal of this conference, the Cognitive. George, my PhD student, he's a co-author. He's used, I think, about 10,000 images. So he scaled it up. He got some convincing results. Now he has to write it. That's the question. Okay, and these are the results. True positive, false positive, true negative. So we missed four images out of 120, which is a pretty good result. In this application, we are using 2 neural networks. The one below that produces the ins, and this is a YOLO, and the one above, which was shown before. It's an in neural network. So this is the end of the very simple application. And now is the good part. Mathematics to see the ontology of these things. The magic symbol is this. This is a letter, it's called Aleph. It's an Aramaic letter. Today, it's used in the Hebrew alphabet only. That's where the letter alpha comes. A. We have it in Spanish and English, comes from Aleph. Now, it was used by mathematicians of the 20th century to show infinity. You know, the infinite thing per excellence are the numbers, but not all the numbers are, all the sets of numbers who are infinite are of the same cardinality, as we say. The The integer numbers have a cardinality aleph 0. Okay, the real numbers have a cardinality aleph 1. So the models that are used by deep learning, due to their parameters, can be aleph 1 many, infinitely many, but aleph 1. Using ins under some assumptions, we can go to that many models, aleph 2. This is the power set of the real numbers. That means that using models with ins, you can have an infinite number of orders, more numbers, not slightly more numbers, infinite number of orders. But this is a theoretical limit. In practice, everything is finite. Even if we say that with bytes of numbers, we can represent the real numbers, we can represent only a finite number of integer real numbers due to the finite word length. But the critical thing here, this is the final conclusion, is that with this type of networks, we can have same number of parameters with fewer neurons. So we can reduce the size of the network. And hopefully, everything will be presented analytically in this publication, which under review. I hope it will be published. So, thank you very much.
Any?
Thank you, Professor. So I had a question. For the examples that failed, any ideas of like when the failures occur? Like, are there any conditions in the images that kind of led to it? Or
Well, no, I cannot answer the question. I don't know. I haven't seen it in detail yet. Thank you very much.
Thanks again. Appreciate it. So let me ask you a question about, so you were showing that the sort of the expressiveness of this space, this Aleph2 versus the Aleph1 that we would have for, you know, the real number based neural networks, you have a lot more expressiveness, you know, infinitely more expressiveness. But you're also claiming that it is more training efficient or energy efficient in some ways, potentially.
I hope so. Speculation.
That's the thing I'm trying to, the largeness of the space, the increase in largeness of the space seems like it may also make the search problem more challenging.
Because I know this the space is not large. It's a superset, strict superset, but the space itself is not larger. What is larger is the number of models implemented. So that's a theoretical limit. We can never reach it in practice due to the finite word length.
Okay, so you're saying because the computational aspect of representing it in computers, that will kind of sort of like there's a little more discontinuities in the space, that the things that you're actually, okay. Yeah, it's interesting. It's interesting to think about, but maybe bigger than my brain can actually compute with. Thank you. It's very interesting.
Yeah, it's a very interesting theory, and I would like to understand it. It's more like a curiosity. If you have like tried to analyze how this the loss behaves given like a different set of parameters, or if you can like reduce the number of parameters to see if, for example, in learning systems such as neural networks, we have like a convex loss. When we see this kind of, I feel like observe some kind of topology or something like this, how this behaves.
Studies and everything, is that the models perform well on models with a large number of parameters. And I think this is a universal truth. It's true in neural networks and also the fuzzy system, usually the so-called type 2 fuzzy systems, perform better. So these are all characterized by a larger number of parameters. So I think that this is the key. And I suggest a method to introduce many parameters with smaller architecture.
Understood.
So there's nothing tested yet, but it's a good guess that this might be the case.
Nice. Thank you very much.
Online.
Okay, thank you so much, Professor Vasilis. Okay. Okay, we have a few minutes more, so let's continue with the next presenter. In this case, we won't follow the schedule because we have extra minutes. So for this stage of the presentations for today, let's receive to Victor Peláez. Okay. ¿Tienes el apuntador? No te pregunto. Okay. ¿Qué pasó? Oh, espérame, que me... O sea, no me sale que no, es así, espera. Que me sacó esto. Ok, ahí está. Ya estoy de vuelta. Puedes controlarla. Listo. Okay.
Okay, thank you. My name is Victor, and I presented this research work. It's titled "Bio-inspired computational model of the perception for detection of simple events from their visual features." Okay, this is our table of contents. Okay, it's I beginning with a question. No? It's how to understand the world. Any intelligent entity that wants to generate appropriate behaviors needs to understand the world. And this understanding represents a multifaceted cognitive process, wherein the continuous stream of perceived information of the environment. This environment stimuli is converted into discrete and actionable units of information. Okay, is the assigned meaning? It's now information. Okay, the complex part is giving it the meaning of that information. Okay, and the event segmentation, this is the principal topic of this research. It's a problem in the time series, refers to the challenge of identifying meaningful boundaries or change points within a continuous stream of temporal data, thereby dividing into discrete and homogeneous segments. This segment is the goal to reveal underlying patterns, states, or events that describe the source of the data. Okay. Ahora, now, sorry. What's the characteristics of the information or that meaning of that data, that discrete? It's multimodal, complexity levels, utilization levels, that is a response, temporality, and formation times. What's the event segmentation? The cognitive process responsible for transforming continuous activity perceived from the world into meaningful events. An event is defined as a time segment in a specific location, perceived by an observer and possessing a distinct beginning and end. And here's the problem. Current AI and cognitive models, despite the need for dynamic world compression, prioritize slow and high-level knowledge processing. This over-reliance prevents them from leveraging faster, lower-level reactive mechanisms, resulting in delayed or inadequate response in real time and unpredictable environments. These are motivations in the robotics and the video analysis and health and security system, or our research. Where's the general objective? Is to design and implement a computational model inspired by neuroscience and psychology that leverage event segmentation to convert visual stimuli into structured multi-level units of experience, enhancing predictable capabilities for problem solving. And where is our proposal? Okay, in the event segmentation theory, it's principles. Where's that principles? But our proposal, it's are that principles. It's a knowledge organization, boundaries, and time scales. Knowledge organization, it's a hierarchical structure, nested and minute. Boundaries, it's hierarchical organized, unexpected change, and conceptual characteristics. When time scales, it's hierarchical organized, sensory regions, high-level modalities, and multimodal areas. And where's the benefit of event segmentation theory for computation? It's improved learning and memory, enhanced prediction and understanding, and handling complex and continuous data. In the knowledge construction and prediction, our proposal is the representation of the knowledge representation is organized by levels of information processing. The sensory systems, okay? The sensory systems, it's us with small events that are then grouped into presemantic and precontextual memory. Okay? Information flows in one direction to feed forward and feeding these units of information from the higher level and feedback to the lower levels. In this work, we will only focus on the lower levels. Okay? Sorry. Our conceptual model, it's presented by this figure, and I can explain the process of the proposal model. The first stage of our model is the model is implementing a bio-inspired input stream, but a stream that simulates the functional architecture of the early visual systems. Okay, it's starting with the preprocessing module in the nucleus, the lateral nucleus geniculus lateral, and which process the RGB channels to extract chromatic information and find spatial details. The processed information, it's to higher modules that replicate the functions of the primary V1 or V2 visual cortex. The next stage is the motion detection and silence filtering. The change between consecutive frames are calculated to identity movement. The difference image is reject the threshold, and the contours are extracted to calculate the area of detected movements. For example, in the case study, if movement is considered relevant, it exceeds a minimum area of 700 pixels. Okay. To determine whether the change due to movement is relevant and compare it between frames, it is necessary to consider a time interval, delta t, between the capture of the first frame and second. If an object moves greater during the interval, it is a velocity minimum, and that velocity minimum, it's assuming that the moving object had as approximately circular shape, and the minimum radius, it's calculated by that formula and delta t that I mentioned previously. Biologically, this mechanism it's useful because it mimics how the human visual system detects meaningful movement in the environment. The MT and MCT areas are specialized in processing information about the direction, speed, and displacement of objects. And the next stage is the feature extraction. When motion is detected, the system extracts the delimited regions and analyzes for a specific color characteristics. In this case, limited to red and blue, okay? Mimicking the feature-sensitive processing of before. This analysis involves converting the image from RGB color space to HSV, its hue saturation value, which allows for more identification of specific colors under varying lighting conditions. And the last stage of our model, it's contextual logging and event logging. Every event that exceeds a minimal threshold of salience is recorded by doing to continuously. The system generates a temporal trace of the visual scene. And that event, the stimulate episodic encoding of special events through attentional salience. Each detected event is recorded with contextual information, including time, location, and semantic relevance. This process is inspired by the coordinated of AI, ACC, and DLPVC areas of the brain. T in this event conceptual information, it's T is the time, Q is the quadrant in which the event occurred, and A is the area in pixels, okay? C is the color of set of color associated with the event, and O is the object label detected in the region, okay? What's the results? In the cases of study, this case study was conducted in a controlled visual environment designed to analyze events involving a person's movement. This scene was monitored by a fixed camera and divided into 16 quadrants, okay, to facilitate spatial tracking and even localization. To evaluate the capacity of the proposed cognitive system by modeling brain areas related to perception, attention, and memory through a case study focused in the segmentation of low-level visual events. The stage of the experiment in our case study is the first stage is low-level salient events are continuously detected. Okay, it's that in the knowledge representation, the lower levels of information. Okay, this stimulus is very fast, and it's a lot of stimuli in the lower level. But organization of this knowledge representation, it's in detected area, okay, for pixels, colors, and quadrant in the information in lower level. And the second stage of the experiment marked the moment when the person get up from a chair, indicating possible goal-oriented behavior and initialization, active segmentation of subsequent events that are temporally and spatially related with shared visual characters, example, dominant color. It's the beginning, the detection of a trigger event labeled as event 0. And the system tracks the person's trajectory by grouping events labeled at event 1. Then final state defined by a significant change in lining corresponding to the activation of the light switch, labeled at event 2. Okay? This state represents the functional closure of an event marked by the detection of the meaningful action or environmental change. For example, a shift in lighting conditions may indicate that a person has moved within the scene to turn a light on or off, completing the event cycle. Okay, this hierarchical classification of events into 3 states. Allows for their segmentation and prioritization based on behavioral, that's a relevance and contextual importance. By distinguish between higher salient events and completion states. In the next stage is the association of quadrants based on visual features. Detected events can be grouped when they share similar visual characteristics, such as color or proximity. This mechanism allows for the construction of more coherent and structured representations from events that may be scattered over time. The system's ability to group events allow it to maintain their identity event when elements appear in distant quadrant that don't know corresponding to a task. It's, for example, these events of this group of quadrants, it's associated for the same salience event, and it's in this stage of the experiment is the color red. Okay, this aggregation is a representation of the next level of the knowledge representation. And segmentation of events in the case study allows us to analyze how a set of events can be grouped to facilitate the segmentation and tracking of events. Through the movement of the person through the environment, the analysis of the collected data focuses on verifying the extent to which the spatial, temporal, and visual grouping criteria captured meaningful sequences revealing patterns in the person's trajectory and their interactions with the space. 403 detected events classified by dominant color, highlighting the abundance of red leveled movements and the inclusion of fine-grained actions like John mentioned, is in the lower level of the stimulus, of the salient stimulus events. And illustrates that figure, it illustrates how salient events are grouped considering the spatial proximity between quadrants. From 430 events, grouping of events in 40 in time and salience related to the number of quadrants associated with a grouping of events. And in the last figure shows how events, in this case, visualization of 30 linked events showing how movement-related sequence begin. Green dot is the beginning of the event, and red dot is when the light turns on. What is the case study insights? It's demonstrated effective segmentation during nonlinear movement patterns, demonstrated real-time event registration, robust to interruptions and activity restarts. And the conclusion is the bio-inspired event segmentation system that we propose enables real-time detection and segmentation of events based on perceptual features like color, spatial location, and temporal continuity. Event chains allow the system to represent the structured and coherent sequence of actions in dynamic environments. Object and quadrant associations support higher level interpretations, improving responsiveness to relevant stimuli. Thank you very much.
Fantastic job, Victor. Thank you so much. Okay.
Thank you. Very good presentation. I have a question. From what I've studied, like event segmentation theory by Sachs tries to segment event using the event boundary, and this event boundary criteria is what your system, the observer, has predicted against what is the next state of the true value that we'll have from the environment. But in your case, from what I understood, you're trying to see if like two states from the environment are having some difference. But shouldn't you like use the predicted state from the agent instead of using like the difference between states in the environment?
In our research, the study is focused on the bottom-up construction of the knowledge or representation or information representation, and the top-down. In our experiment, is bottom-up. It's the capture of the stimulus in very small timestamps. Okay, and from the top-down information, it's from attention that we search red color and movement object. Okay, it's for focus on that that issue of the experiment.
I understood, but shouldn't the top-down try to like predict the next state of the environment, like using, for example, a Kalman filter or something like this?
Sorry, this one.
For example, shouldn't like the top-down system try to predict the next step of the environment instead of trying to search what are the specific features that you're tracking?
Yeah, in our experiment, the predictive it's to relation of the in that case the quadrants, no, of the environment. If no related in the adjacent quadrant, it's now sharing the same characteristics.
Okay.
Okay.
Thank you very much.
Thank you.
It was a very ambitious presentation. Thank you very much. One question regarding the granularity. How did you decide the number of quadrants? 16 or whatever? Thanks.
No, the criteria is just
Heuristic.
yeah.
Okay, so first, feliz cumpleaños.
Thank you, doctor.
But very interesting. One of the things I was curious about when you were showing your model diagram, you had V1, V2, MT, the data structures and the processing that's happening in each one of those levels. Could you talk just briefly about that? Are you going from something that's more like a retinatopic kind of representation over to something that might be more so that your tuple, the E tuple that has your area and object, so you've switched away from something that's sort of two-dimensional, maybe topographic. Maybe earlier you have something that's more like almost like a retinatopic kind of map. Can you explain a little more about the data structure?
The data structure that that we have it's
It's like a two-dimensional.
we only naming that units of information. It's not specific data structure. Just we have a radio of the pixels of the area, because the visual system is the retinotopical mapping, and it's for the circle. Okay, and in the space, in the camera space, it's a quadrant, and it's convert that information, that pixels in quadrant, that radio, like the system that the visual system used to structure the information.
Okay. So you have one where it's the pixel level, and then it's converted over to your tuple.
Yeah, the RGB colors, so the RGB representation, it's convert to the a number, no? That for example, red, it's any percent of the of a red, percent of green, percent of blue, and this represent the red color, and that information it's to establish the top-down information. Is red color and move the object. It's just you search only for that stimuli, not other.
Got it. Thank you. Appreciate it.
You're welcome.
Any other? No? Okay. Thank you, Victor. Congrats.
Well, let's have a 20 minutes break. So we'll be back at 11:40 Mexico City time. But for the attendance, we have a little announcement. Yeah, let's have a coffee break now. For the virtual attendees, we will see you within 20 minutes. Thank you.
Thank you, everyone. The next exposer is Francisco Lopez.
Sorry. Hi, my name is Francisco. Happy to be here today. Today I would like to talk about this paper. Its inclusion as adaptive threshold on a inspired computational model of attention to improve adaptability in artificial intelligence. This is the content of the presentation. And I would like to start mention that I'm working in quadruple architecture. We abstract the functionality of the brain process and representing like a cognitive function. Now I am working in attention. And I have a question. Why is attention important for the human performance? Well, first, we need to know that the human can process multiple sensory inputs and dynamically adjust importance when stimulus become relevant to the given objective. For example, when you are driving, you need to have a set of some things or things that are important. You give more importance to traffic things than music, for example. We can detect a signal, for example, a traffic signal. In this case, you decide to stop your car. But what happened? Other thing is very important. We have a limited resource. This is important because we don't have give the more relevance to a lot of the things that appear in the environment. We need to delimitate and precise something relation to the task. For example, what happened is a person when you are driving appear from you. We need to stop the tasks that our developer we are doing and avoid the accident in this case. This is a relation with the threshold. Threshold is to define a minimum intensity of the stimulus that's mere research to be detected by the sensory system. This is very important because attention function, has a key role filtering stimuli to indicate which stimuli should be processed and which should be ignored. This is important because agents or a system we have the ability to adjust this threshold dynamic cannot adapt its goal to change in the environment or modify in the task. For example, a system capable of adjusting a priority of the level of the stimulus using a dynamic threshold can focus processing on stimuli that are silent or relevant to a task, thereby improving the performance on the attention system. For example, external cue make or can be changed the tasks that I'm doing, but it's important to understand, it's important first to understand that we have the flexibility to change the tasks. And why it's important to attend this kind of work? First, my motivation is contribute the cognitive science, improve adaptability of the virtual agents, as system for care of the vulnerable group of persons. Now, we need to know how function the brain to change the priority and adapt the threshold. The threshold is related with first 3 networks: the Falmouth network, the salience network, and central executive network. Our brain has many interconnected nodes that perform a function, and 3 networks mentioned about is a simpler thing. We can say that first, silent network detecting and prioritizing stimuli based on the silence. For example, when appear a person, the Falmouth network provided the default values to the threshold. For example, when you're walking, you're thinking about, I don't know, what is the dinner or other things, but you have a default values. These values represent maybe there are something important in the moment, but this something can be changed. And a central executive network. This allows attention threshold to be adjusted strategically for favor to present information that is related to the current goal. When analyze the state of the art, we can find this. First, we can find that the there is a limited representation of the structure to represent adaptive threshold. Also, we can see that the central execution network has been studied more extensively than the other network, like the Falmouth network. But we can find that the Falmouth network is represented like way static. Why is important? We have the flexibility to change the values, the tax or the stimulus related to the tax. This results in limited ability to adapt agent behavior based on external signal. Like a conclusion of the state of the art, although several community architecture integrate mechanisms, the particular representative of the function about these networks, a fully integrated system for dynamic adaptive threshold modulation is still lacking. In particular, the Falmouth network. It represents a structure, and we need to consider how external cue can trigger a change the tax. Now, the proposal is this. The aim of this work is to provide agents with the ability to adapt the relevance of the stimulus using adaptive threshold. Our proposal suggests this. First, using a structure, in this case, Cayenne. Remember, we have a limited resource, and we need to define which stimulus are important, which contain a set of DI to represent those are relevant and give an attack segment. This is only for attack segment. This can be changed. For example, this structure has this element. For example, the letter E is a stimulus associated with a threshold. It's like a label, only that. For example, when you receive information or signal of the environment, we need to, well, this information that is received need pass a threshold. In this case, the threshold is represented range 0 to 1. For example, if right now appear apple, why apple appear right now? Well, in this case, it's novel for us. In this case, the silent network make an innovation in the Falmouth network and activation in central execution network. For example, we need to attend the stimulus. In this case, it's apple. This is related with bottom-up attention because we process according to the salience or physical salience of the stimulus. In this case, maybe it's apple red. Then we need to understand that the file network provides a central execution network information. In this case, is the file value is this value used to represent the threshold and receive charities associated with the tax. For example, in this case, apple is color red or green, shape is round, and texture is smooth. Then, how to produce top-down attention. This is very important because we receive signal of the environment, but in what moment the signal make or change the behavior of the agents. In this case, when you have a representation of the stimulus in your brain, in this case, it's very simple. For example, the central network send information as silent network, and this make that we have a direction, attention, or attention direct with the goal. In this case, we have a perception, or we have a structure in our mind. Other important thing is how to change the value of the threshold. In this case, we propose a simple function. In this case, consider the current value of the threshold, the default value, and in this case, this value is related to a C. C in this case is the stimulus is related with the tax or no is related with the tax. In this case, we reduce the operation to reduce the computational cost. And it's important to mention that the few times that the stimulus appears is more relevant than the other ones, or if the stimulus appears several times, the importance reduce. For this reason, the few times the threshold or the threshold is reduced. If the value of the threshold is near to 0, means that it's more sensitive to detect or attend that stimulus. If it's near to the 1, it needs more relevant salient to be attended. But when the stimulus continue appear 1, 2, or 3 times, the important is less. This is important to mention because if you continue to reduce at the same way, we have problems maybe in the future to determine which is important or why it's important. Now, in the case study, the objective of this case study is to evaluate how the agent identifies relevant events in relation to the task, in this case, detect false. And the hypothesis is a system capable of dynamic modify its threshold value can adapt in the sensitive, allowing detecting a stimulus relevant to a task. Well, in this case, we simulate a smart house, for example. In this case, consider 5 interconnected rooms. In this case, kitchen, gym, bedroom, living room, and game room. We try to help, in this case, a elder person. For this reason, I decided this experiment. The idea is the movement of the elder person is simulated. Only is this experiment. The event is divided in 2 events. The first is tax-related events. In this case, is 32%. For example, attend a false or immobile in the people. In which case, if the people is immobile, maybe die, I don't know, for example. Not tax-related with the event. In this case, 48%. For example, environment zones, incoming calls, or turning on the lights. First, initially, the threshold for detecting files was set in 0.5, and immobility event start in 0.4. It's important to mention we adjust not only the files. For example, in this case, in the experiment, this event represented a file in the person. But we need to consider that we also need to modify in this case, threshold related with the tax. Why is important? If you only give priority one event, okay, I need to be more quicker. We need to change the close event or show close threshold to improve the function of the system. And the end of the event, the file threshold was modified by 0.41 and was moved, in this case, model threshold was modified by 0.32. This can detect events or events with salience that the first can be detected for the system. Other important thing is when the experiment, the change of the threshold value become progressively smaller over time. In the case that the first simulation have the greatest impact on the system. As events are repeated, the effect of the threshold setting decrease, event tones and events are more extensive. This means that the agent gives a low priority because it is no longer as novel as when its fear appeared. Result of the case study, dynamic threshold adjustment, the agent modified the sensitivity to detect event that initially did not reset the threshold. Adjusting the priority of the task to say the stimulus beyond that the detected stimulus improved. The identification of relevant event when consider contextual variables. And there are areas of opportunity. For example, in the experiment, we can detect a critical zone management. For example, in this case, the living room and bedroom identify as priority areas for false detection. Other is exploring external queue. This allows to identify which room is potential observed or external queue can be changed the tags and intensity of unrelated stimulus, light and noise in the kitchen. This is important because we can generate alarm to give information. I hope to say the person is help to the other people. For conclusion, this work presents a model adaptive attentional threshold inspired by this network and regulates sensitivity according to a stimulus contextual relevance. Unlike static system, the model allows an agent to balance internal goals and external demands. But we know that we have a lot of work to do. For this reason, the future work is we plan to evaluate the scalability of the model in real and dynamic environment. Adjust the threshold based on experience. This is important because we can make a routine of the person, and this is important for people to know if there are or appear situations that are not considered in the routine. We also investigate the role of this adaptive threshold in long-term behavior about the routines. The reference, and thank you for your attention.
Amazing topic, Francisco. Thank you for sharing with us. Okay.
Thank you very much. I think this is an important topic, and it was great to hear about it. I was curious about, so with LIDA, for example, the agent's motivational system, the basic drives of the agent, it's deeply intertwined with the attentional mechanism for what's important at a particular moment. And so LIDA has a little bit of dynamic attention based upon that. So in your case, the basic drives of the agents, how does that modulate your attention mechanism, and how does it change? So say, for example, I have a basic drive to satiety, to be full and not to be hungry. How does that change, or do you have something that changes right now based upon the agent's internal state and its motivations?
You refer intrinsic motivation, right?
Yeah, so like the motivational system, its basic drives and its changes over time in terms of like a homeostasis, kind of like being full, being hungry, being thirsty, and fulfilling those things. How does that stuff influence attention?
That's a great question. Right now, I am working with a co-worker about this topic. In this case, first, we try to modulate the events related with the other people. But about your question, we try to modify, for example, in the function. It's an idea, for example. In this case, we have a context. But this context only is one value. But we can add other parameters, for example, intrinsic motivation, to change. In this case, only I consider external cues. But in the future, I consider internal cues.
Okay. Yeah, and context could include those internal signals as well, certainly, or it could be a separate one. But that's great. The other question, let's sneak one in. So you had the example of the person about to be hit by the car. And so there's an element of prediction of future states. It's not just the person, because if the person were on a sidewalk, no problem. Person in front of the car, that's a problem. So when you're trying to figure out the tensional threshold associated with an event, are you in a lot of cases forced to predict future state?
Yes, for example, the work that my partner Victor present, we consider a function to determine the events that, for example, in that case, turn the lights, right? But what happened in the case of the person appear from you? In this case, we need to consider, for example, to stop the current tax, right? Yeah. In this case, for example, if you are drive, maybe you can to get, or you try to go to your work. In that case, I consider that it is relevant to have a function, but I try to generalize the function, because maybe it's a person, but maybe it's a dog, or maybe it's other thing. For the reason I think, in this case, when I say this function, I don't mention in the presentation, but this tuple or this structure has a stimulus relate with the task, but I have a set of stimulus that I know relate to the task.
Okay. So
for example, in the experiment, it's a noise or sounds, for example.
So right now, that task-specific kinds of thresholds changes, that's the main.
Yes.
Makes sense. Cool. Thank you.
Hi, very nice work. I was in a doubt that in more complex cases, for example, when you need to change your sensor devices to different positions. Imagine, for example, that I am here and I just take a noise from here. I need to move my camera to another position. Do you think that the same model could handle this kind of situation, or you should change the model and put some more issues on it such that you can make this movement of your sensory devices to pick up the right information where you need?
Okay, great question. In this case, we need to remember that we have a bottom of attention and top down attention. In this case, the experiment is try to get a smart house. We are trying to work different sensor, for example, cameras, sensor to detect the
But
noise.
you're thinking on cameras that can move and focus.
Exactly.
And okay.
For example, this camera follow me when I try, well, I walk, for example.
Okay.
In this case, the idea is use these kind of cameras, use other sensors to improve the ability to the agents to detect external cues.
Okay. Okay. Thank you.
Okay.
Any other?
Francisco, when I hear the word adapting, my question is, how do you use the a priori information or the a priori knowledge of the environment in the adapting mechanism?
Sorry, I don't hear the first part of the question. Can you repeat?
How do you manage the a priori information or the a priori knowledge you have about the environment in the adaptation mechanism?
Okay, this information is provided, in this case, from the default mode network. We need the assumption that we have values to determine. Okay, the idea is we have a default values for the stimulus that are in the environment. Yes, remember this is the idea is to try to have a smart house and smart home or smart house. We need to define the something that are in the smart house. For the reason we have assumption default values are considered.
Okay. Amazing job, Francisco. Thank you so much.
Well, thank you so much, Francisco. Okay, so let's continue with the next presenter. The next speaker is Bruno Silva. Bruno, are you ready?
Yes, can everyone hear me?
Okay, we can hear you and we can see your screen, so let's go start.
Okay. Hi everyone, my name is Bruno Silva. I am a PhD student at Unicamp and also a member of the Artificial Intelligence Cognitive Architectures Hub. And today I represent the representing episodes space-time experience for cognitive architectures. And this project was also done mainly by me, Eduardo Camargo, and Professor Goodwin, that is on the audience today. And the motivation, the idea from this work started from the question on how can an agent represent experience and gather from existence. And we are interested in defining a knowledge representation that can allow an intelligent agent to represent existence in a general form. And this would in turn allow agents to observe events from its environment and improve its own behavior over time. And from that, we derive our general goal for this specific work that would be how to encode the information received by an agent into episodes representations that can represent fragments of existence. And to start answering these questions, we begin by defining what we understand as existence itself was said by Professor Gooding yesterday at the keynote. But we see existence as being the totals of space-time continuum. So the agent is immersed in an environment that expands the total space-time continuum the agent could experience over its lifetime. And from that, we argue that from observation point of view, existence can be fragmented into episodes that consist of specific regions of space and time intervals, which in turn can be fragmented into smaller and smaller space-time regions, such as, I don't know, specific cities, building rooms, or specific time intervals, years, weeks, days, and hours. And in that way, existence is a episode containing multiple other sub-episodes from sub-regions in space-time. And when we keep fragmenting that, we reach the limit where the time interval tends to zero, and we can obtain a situation which is a single snapshot of a space region. Continuing this segmentation in smaller space region, we reach a set of entities that compose the situation. And by fragmenting these entities, we found the characteristics that compose them, such as color, position, things like that. And this will form a dependence of complex representation, such as episodes, on simpler ones, such as characteristics and entities. So to summarizing our proposal here, episodes, situations, entities, and characteristics are the main primitives to construct our knowledge representation of existence. So before constructing our computation model of space-time fragments as episodes, we first look at other ways that episodes are represented in cognitive architectures. So at the literature, we found most commonly episode represented as sequence of states, not all of them, but most commonly. And these states may include external or internal information to the agent, and can be collected just as simple sequential snapshots of the agent knowledge over time, or they can be integrated into more complex, like probabilistic state transition graphs. But the main concern that we have is that usually there are no specification of the time interval of events and episodes. So the temporal information delineating when an episode started or ended can be lost, and therefore we would not have the space-time fragmentation representation that we actually seek. So we move to our knowledge representation, and it starts with the computation ideas. So to construct our knowledge representation for experience from existence, we take our previous studies that was shown yesterday as well on an ontology of reality called computation ideas. So every idea usually has a name, which is a symbol that can reference this idea. It also has a value that can be a numeric key or a reference symbol to another idea, or even a null value. And we also have a category name. And this category name will determine one of the types of the ideas in the existence: episodes, situations, entity, and characteristics. And the last important element on idea would be the index. It's the allow the construction of more complex idea, when idea can reference and be composed of other simpler ideas. So therefore, the index is the capability of a computation idea that will allow us to construct episode ideas as fragments of another situations, and situations as a set of entities, and so on. And finally, idea may also be a general category. We are not talking about habits on this presentation, but just the categories. By defining a membership function, which takes an idea and return a value indicating if the idea belongs to the set or not. So we can take example from a category of a chair, and given examples of entity ideas, the membership function would dictate if the entity is a chair or not. And with the computational ideas representation as a framework, we can tackle the problem of representing observational episodes from our perspective of space-time fragments of existence. And in that sense, observation episodes we take as being changes that happen to a single entity and are observed by an agent without inferring any causal relation of the event. And this change will occur in a space region limited by the occupancy of this entity, and a time interval delimited by the start and end of this change. Here we take a change as being the transformation that occurs to a value of an entity's characteristics. So like change position, changing temperature, or things like that. This observational episode can then be represented by a sequence of situation ideas. The first situation we name initial situation, the last one is the final situation, and the other steps are the intermediate situations. Each situation specifies the entity suffering the change, as well as a time step, meaning that the situation of an episode refers to the same entity with the specific characteristics value at that time. And the representational part of the scheme that we propose comes from the information we can attach to the observation episode idea at the root. As an example that would be shown in the experiments, an episode category can be associated with the episode idea indicating the semantic information of the change that occurred during the episode. For example, if it was a linear or an exponential change, if it was positional translation, maybe temperature raise or things like that. And this information can be processed during the agent inference and later incorporated into the episode for episode buffer in an architecture or long-term memory. And this will carry more complex semantic information than just a mere sequence of states. And given these frameworks, we formulate an experiment in simulated environment to showcase the use of the episode encoding. The environment that we use is a simple single room containing our agent in green at the top. We have our agent here. We have the Discord knowledge representation. And also two other agents that we call actors, and they just execute predetermined set of movements in the environment. The first one in red on the left, it goes to the right, comes back to the start position, and then does a zigzag motion in front of the agent. And it's important to know that the zigzag motion is continuous. There is no pause during the curves of the zigzag. And the second agent on the right is just go to the right and then come back to the left. And the goal is for the agent in green to observe these episodes and encode them using our proposed methods. So the main agent possesses a simple cognitive architecture that does the sensor processing and creates these observed episodes. The architecture was developed using cognitive system toolkit and is composed of codelet. They are stateless process units showing rectangles and memory objects. They store input and output information and they are shown in circles. So first, the agent receives sensory information directly from the simulation. So they do not process raw pixel information, but rather symbolic information about each individual object in its field of view. And the agent can then categorize each sensed object into walls or actors. This is done by using category ideas that define a membership function, as said previously, and stored in the walls and actors memory objects. These entities will possess information of color, position, and size, both for walls and actors itself. After that, the detected objects are accumulated in the situation that basically captures the spatial disposition of them into a snapshot of the observation and accumulates it into a buffer of situations. And finally, a coder looks at this buffer of recent situations and processes it to detect any changes that have occurred in the values of the characteristics of each object. Basically looking at how the entity's characteristics change over time. And these changes indicate that an episode is starting or just continuing or episode ends. And the most important factor here is how we define that a relevant change occurred to form this kind of episodes. This is done by using categories of episode ideas, and specifically we use two types we design two episode categories on our experiment that look to change in object positions. So we are basically detecting if the objects, the actors itself, are moving in the environment. And the two categories are generic movement and linear movement. The generic movement says that a given sequence of situations is an observational episode if any kind of change occurs in the position value in a continual time interval. And the linear movement does a very similar process, but the change of position have to be in a straight line. So if there is a curve, the episode will be segmented into two different time intervals. And when we take a look at the initial and final position of the actors for each detected episode during our experiments, we can see the difference between how these two categories behave. So the difference is made very clear by the zigzag movement from actor A. And the generic movement category on the left, it concatenates the entire movement of the zigzag into a single change, shown by the arrow to A that start on the here and here. And on the other hand, the linear movement category on the right split every continual movement of the agent into straight lines segments. So furthermore, if instead of looking just at the initial and the final position of on the initial and final situations, if we plot the difference in position between each intermediate situation, we can clearly observe how the movement was concatenated and that the agent did, with the generic movement, did observe every zig and every zag of the actor, but on the high-level representation of the episode, the movement summarized as a simple linear movement between 2 points. And this shows that if we compacted the representation by removing these intermediate situations and remaining only the initial and final position of the observed episodes that were detected, we would get less information with the generic movement on the left, but very compact because we are just removing a lot of information. And we would get a more detailed information with the linear movement on the right. And this goes to demonstrate the capability of the knowledge representation, specifically the category of episode ideas that we are showcasing here, to represent semantic information as these category ideas and how these category ideas can influence the interpretation of an agent has of a given event. So meaning that the experience that the agent gathers from the world could change if the categories in some moment in the future would change, and in turn change the structural observation of the environment. So we are trying to show here how can the gathered information can be used as actually experience to modify categories, and this category will in turn modify how the agent itself perceives the world. So lastly, as future works, we would like to explore models of simulated episodic information, such as imagining episodes and counterfactuals that could be constructed when the agents gather experience over time. But to do that, we acknowledge that we have to improve our knowledge representation and to enable this accurate simulation of hypothetical episodes. So it will be necessary to explore how causal relations can be represented in the framework we propose, touching as well on questions on how to incorporate concepts of agent and affordance into this representation, into this episode representation. So this was everything that I had to say today. Thank you very much for the attention. And on the left, there's a QR code for the GitHub code repository from this presentation, so you can take a look on how we did the ideas and how you can run the simulation yourself. And also acknowledge that this project was supported by the Brazilian Ministry of Science, Technology, and Innovation. Thank you very much.
Thank you, Irwin. Does anyone have questions? Okay. We have one.
Hi, my name is Andrew Nuxall. I have a question about your compacting. I was unclear in the results. You were talking about compacting the episodes. Is that just a compaction, the identical meaning, in terms of like information theory, where it's the same information, it's just in a smaller form? Or is that a form of, or is it a forgetting mechanism? Or is it a way to encode, like one of the things about episodic memory is that some episodes can be longer than others. The episode you might have while you're sleeping can be very different than an episode you might have in a car chase. Is any of those relevant, or am I on the wrong track?
No, that's correct. We don't go into like information theory on how useful, how good the compact information is, but it's on this idea of also forgetting as well. Because when we have, for example, on the right, we have this more high-level category of semantic information of what is a linear movement. So if we observe a linear movement on the world, we do not have to remember as every single frame of position where the moving object was. We can just remember it started here, it ended here, and the movement was linear. So we go from just a sequence of frames to three basic information, start and end position, and what type of movement, and then we can reconstruct, using this idea of episodic memory, we can reconstruct the observed episodes from what we stored in our memory. So it will be exactly that idea of how can we compact this information, and what we're trying to show here, that depending on this high-level category that we have of episode, the compacted representation can be different. So if you change, of course, what you can understand of the world, you change how you store the information from the world.
If I may, I have a second question. One of the things I've observed about episodic or episodes is that they, and this is, you can see this in psychological observations, and also it kind of makes sense, is that there's a hierarchical nature to episodic memory. Right now I'm having an episode of asking you a question, which is part of a broader idea of that my Saturday at BICA, which is sort of a part of a broader episode of the week I spent in Puerto Vallarta, et cetera, et cetera. Does this mechanism have any support for that kind of representation? And related to that is, one thing that's really important is trying to find an episode. You're given a memory cue. How do you find that episode? Often a structure like this can really make that very efficient. And I'm done asking questions. Thanks.
Yes, we did not explore that idea yet, but we're thinking about in the future, because the idea of representing existence as fragmentation of episodes has intrinsically the idea of an episode can be the composition of other episodes. So you can have a bigger conference episode that is composed of smaller episodes for each day, and each day is decomposed or before and after coffee break, and each one of these is in the individual presentation and things like that. So it would be possible to do this hierarchical representation. We are not exploring yet how to retrieve this information. It's would be a bit more depending on how we end up implementing that as a graph, a sequence, or tuples, and how if you end up embedding this in some high-level dimensional space. But the idea of the hierarchy representation is on our mind as well.
Okay, any other question?
Appreciate it. Good presentation. Thank you very much. I have a question about, so with representing episodes, one of the things that you had mentioned related to the survey you've done on other cognitive architectures is that they had sort of state transitions, but they didn't deal with time. So you mentioned that you have these different sort of time ticks that you're using to associate with the different situations or states. Could you go into a little more detail about the nature of that? Is it relative to the episode itself, where time starts at 0 for the episode? Is it an absolute reckoning of time, and is it discrete, continuous? Could you give us a little more into that?
Yes, we're doing the sticks and we're using basically the clock of the simulation. So the simulation starts at 0 and go on. And at the moment, we are using absolute values. So if the episode started at the second 10 and goes to 20, that's the start and final time interval. But this is also an idea of having this interval. It can be transformed to relative times, and then we can later compose multiple episodes with time relations between them. So you can say we have simple episodes like this, or like was mentioned before, like each day of the conference, and then we can compose these in our more complex episodes that include other episodes. And since we have the idea of how much time each episode took, we can say that this one was before this one, or during this one, or when this ended, the other one started soon after, and things like that. So we want this time information, not and it's not, this information is also not just for the whole scene, for the whole mental state of the agent, but to have an episode for each object. So there are multiple episodes going at the same time, and we can time these episodes and do this relation. So we can say if objects start moving together with another object, or they are moving one after another, they are moving just in a very different time interval and things like that.
Okay. Thank you. Appreciate it.
Thank you, Doctor. That's all. Thank you.
Bruno. Okay, thank you so much, Bruno, and congratulations.
Thank you.
Well, let's continue with the presentation that we performed by Yuji Sakabe.
Thank you very much. Hello, everyone. Thank you very much for having me. So I'm going to be presenting, oops, I think something, no, I think everything is okay. So I'm going to present an episode encoding mechanism for cognitive architectures. So the main motivation that we have is that episodic memory, the memory that we have about events, is a core component of the human cognitive systems. Tuvin, who discovered episodic memory, states that it describes episodic memory as this true marvel of nature. And it allows us to relive past experiences and use this knowledge to solve problems, make predictions, contextualize our present situation, and enhance other cognitive abilities. And this episodic memory is not only important for us as humans, and also we might say that animals have, but this is a question of debate, but it is important also to artificial agents, as pointed out by Nuxo and Lard. Nuxo is here, actually. And episodic memory, they noted that episodic memory could support several cognitive abilities, such as action modeling, decision-making, learning from past experiences, and virtual sensing, which is like completing the information we have from the environment from previous information from episodic memory. But we have like a main limitation of the models that we've seen so far. That is, most episodic memory models encode episodes simply as a sequence of the agent's observations or sequence of the agent's internal states. So what does this mean? So we are going to here make the distinction between what are state-based episodes and scene-based episodes. So according to Castro and Goodwin, who is my supervisor, there are two types of episodes: state-based episodes and scene-based episodes. So state-based episodes are the ones that I talked right now. So the ones that are represented as sequence of the agent's internal states. So for example, in Isaac and Swar, you can see that basically what you're doing here is taking snapshots from the agent's working memory and adding here then as a sequence in long-term memory. And of course, this comes with pros, which is pretty simple to encode. But at the long term, we have like a high memory cost, and doing retrieval becomes harder. And also, it's harder to integrate directly with higher level cognitive mechanisms, since every time you are going to use this information for example, planning and reasoning, we will require you to do this kind of processing. So you'll have like a processing overhead for interpreting the information that you had encoded in this state-based representation. And on the other side, scene-based episodes are, we can see the scene-based episodes as interpreted versions of state-based episodes. So scene-based episodes encode episodes through space and time. This is very important. Into experiences, into high-level semantic representations, which we call scenes. And the scenes contain high-level elements such as objects, their properties, and also events and episodes. And the issue with this kind of representation, and what we believe is the reason why we don't have much of this representation in the literature, is because it's very complex to figure out how we do this kind of interpretation and abstraction into high-level elements, as I said before. So, and the good part is it is more memory efficient, but it also very good for integrating with high-level cognitive functions, as I will show in my experiments. I think it's not working. Okay. So in this work, we introduce the episode tracker module, a reusable framework, so everyone here can make your own version of the episode tracker module and fidget the way that you like, and design it to integrate the cognitive systems toolkit. That is the toolkit that we have in our research group to build cognitive architectures. And the episode tracker module enables encoding, as I said before, the sensory information across time and space into high-level semantic representations, which I defined earlier, scene-based episodes. These episodes are a byproduct of the perceptual process, and they capture the agent's ongoing experience. So it's the current agent's understanding about the world that it's interpreting and perceiving in real time. So right now we will explain the episode tracker module, and something that is very different, very difficult in this kind of encoding mechanism is that we need to have like a specific type of knowledge representation that can address the issues that I said before. So for this, we use guarding force conceptual spaces as our main inspirations. So it's a very beautiful theory actually, but I don't have time like to go like really in deep in the theory, so I'll give like a surface level introduction to guarding force. But the idea is that we represent concepts. Guarding force has discovered that we represent concepts with some kind of geometric regularities in this space, which he calls the conceptual space. So I'm not going over here the building blocks of this theory, but the idea is that we have some properties which can be represented. For example, the property of color can be represented by a point when it is a specific, for example, shade of red. And when we have like all containing shades of red, we can represent this in this conceptual space as a region, a convex region in this conceptual space. And when we have different sets of properties, for example, here, a certain size and a certain color of red, we can represent, for example, the object apple. And we can represent also the category of apple when you use convex spaces. Events in this representation are represented as vectors. So let's suppose we have here this apple that has been crushed. So it's going to decrease its height and increase its width. So we can represent like the transition between property state 1 and property state 2 as this vector here. And episodes are represented as interpreted versions of these events, contextualized actually versions of those events, where we have an agent, which is an object, this case here, the hydraulic press head, a force, which is like not necessarily a physical force, but the changing position here, the patient, which is the apple, and finally the result here vector, which is the apple being crushed. So one thing that is very good about Guarded Force is Guarded Force provides us a schema for doing knowledge of representation. But unfortunately, Guarded Force doesn't provide us what is the way that we represent, what is the way that we can build this kind of representations over time. So it is not very mechanistic. It's more about what is the ontology and the schema that we use. So for addressing this issue, we got a lot of inspirations for cognitive and experimental psychology, and we built this pipeline, which uses first, the agent will receive sensory information from the environment. Then we are going to use principles of object perception from Spelk, and her theory is actually how we constitute what is the unity of an object without we having like predefined categories earlier. So she studies infants with, I think, 6 months old for this. And later we have these objects, and now we have to understand how do we interpret the events and detect the events that these objects suffer over time. And then we have the representation of events. Here we use event segmentation theory by Zaks. And then we use these events and try to interpret the causal relationship between events using perception of causality by Michaud. And finally, this whole framework here is analogous to the episodic buffer from Badley. And in Badley's multi-component model of working memory. And of course, this is in working memory. So our main work is addressing this part here, the encoding, while we will have here storage, of course, encoding, storage here, and retrieval back, because some long-term episodic memories may be useful for enhancing this process here. So that's the main idea. This is the architecture. This is the design of our architecture using the CST, the Cognitive Systems Toolkit, but we don't have time to explain here. And also the representation in ideas, as Bruno and Ricardo has presented yesterday. So the experiments that we made are first. So first we did a gameplay experiment that is very interesting actually. So the objective was to validate whether the episode tracker module can encode those multiple objects and their respective events and causal episodes. So for this we used the Atari River Raid gameplay environment implemented using Gymnasium, which is a library for reinforcement learning in Python. And the agent actually acted as an observer. So the agent is not playing the Atari River Raid game, this vertical shooting game. It is actually watching us play and trying to make sense of what is watching. And we developed some visualization tools to transform these ideas that are being interpreted to visual representation again. So then we can debug and see if they are like correctly assigned or not. And here we can see the agents correctly tracking the objects. Yeah, we cannot see here, but we have here numbers for each object, and it's being correctly tracked. Objects which have the same category have the same color, and also here we have vectors that we cannot see that are representing the events from these objects here in real time. And we identified and documented a lot of the limitations that we have here in my master thesis that I can reference later. And the most important part, as I said before, is that these representations in these high-level representations are very important for interfacing with high-level cognitive functions. And so for assessing if this was actually working, we designed a Q&A mechanism, so question and answer mechanism, which has like predefined questions, and based on the information that episode tracker is encoding, is going to try to answer those questions. And for this, we created a data set with 10 gameplay sessions, and I also annotated by hand all the ground truth answers for all the questions. So I have 4 main questions here that I'm going to present here. So the first question is how many objects of each class appear during the gameplay session. So the idea here is to see if the episode tracker module can count and assign correctly classes for each one of the objects. Other question is how many objects of each class were destroyed by missiles during the gameplay session. So the idea is we are trying to track some kind of causality here. So not only which object was destroyed, but which one was destroyed caused by the missile launch event. And here we cannot see here the results, but we are using here the relative mean absolute error, which is like the ratio of miscounting. And we have like here good results. We have here more or less, could say like 10% of error. Here in the worst case scenario is like 15% of error. So it is like according to our standards of what we believe that it would be like not robust, but as a first implementation. And third question we have, and those are more tricky, are what were the timestamps indicating the appearance and disappearance of the second field depot that passes in the game, and what was the time interval of its motion. And this captures the temporal intervals of the events associated with the same object, in this case, the field depot. And we also have this question here, what were the time intervals between the bridge's appearances, because we have a bridge in this game, and we have to destroy this bridge, and what is the time interval between this bridge appearing, the missile launch, and the missile launch, and the destruction of this bridge. The time intervals are here are not very important. The important part is that we can use some kind of this little information here, and it can backtrack from memory what was the causal chain that caused the destruction of the bridge. And I'm not going to explain the metrics here because the overall result, it captures perfectly the intervals from these events, and also the appearance and disappearance got like frame perfect results. Of course, because it works a lot in heuristics, so it was already like predicted that we'll behave this way. That's why I say the most important thing is not that how well it is answering, but it can answer because of this its episode representation. So the conclusion, we developed an episode encoding mechanism that can transform sensory data in scene-based episodes. This representation is based in conceptual spaces from Garden Force, and the mechanism is based from insights from psychology, from experimental and cognitive psychology. So our experiments here validated the importance of the scene-based representations for interacting with high-level cognitive functions. And lastly, and I think this is very interesting, you can say, oh, this is only important for like explicit kind of knowledge. But what we did here, we used this encoding of the episode tracker module and applied within a reinforcement learning framework. So we replaced the CNNs, the convolutional neural networks encoding, in a DQN-based agent. And the idea was the episode tracker was going to feed the DQN directly using our representation. And it could maintain the same performance as the CNN, but reducing the input complexity from the input. And this suggests that cognitive modules like the episode tracker module can enhance both efficiency and transparency in this learning system, and acting as a neurosymbolic, make this neurosymbolic mechanism for learning systems. So yeah, that's it. Sorry if I speak very fast.
Thank you, Eduardo. That was amazing. Any questions?
Thank you, Eduardo. Your presentation was very interesting. Only I have a question. For example, do you consider the brain in different levels? For example, if I get up from my chair right now, we can mean that or something. But if I raise my hands, maybe it's other events. Maybe if I move my finger, it's other events. You consider event at different levels?
Yeah, actually, they are all in the same level, but I also agree with that events in real applications and in our cognitive system should have this kind of hierarchical representation, but we don't address this. Actually, for me, this is like the work for my master thesis, and I created like a 10-page documentation of all the things that I think are open problems, and this I think is the main one. This hierarchical representation of events, but also objects is very hard, so we are not addressing here, but I fully agree that it's a very important issue.
Okay, thank you.
Very topic, Eduardo. I just have one. In the GAD4 model, can we represent subjective experience? I don't know, including many features of the object.
Actually, in its original framework, I don't remember from his book reading about this. And I think also what Garforce doesn't address is, for example, attention, emotion. All of this is disregarded, I think, in his work. He's more concerned about the ontology for understanding, but as he is ignoring like what are the process of understanding, it is not addressing like what like feature is more important from the observer's mind than the other feature, or what is the subjective experience from the observer, which I think is very important, but in his representation, he doesn't address it.
Eduardo, thank you for your presentation. My question is how you express or represent the knowledge or the information in our proposal.
The knowledge, okay, so it is pretty hard, I'm not gonna lie, but because it is like, so I'll try to explain by giving this example because I think it's easier to understand how it's built, to understand how it works. So first, let's use it here. So this is our main knowledge representation schema. So first we have objects, which has like an ID, a category, which is represented by string, but we follow Barsalou's actually concept of category. So any category that we have here, it is not only used to discretize if an object belongs or not belongs to a category, but also can simulate an instance of that category. We also have here, there's the predefined features that I've chosen. So we have like the bounding rectangle and the center position, the size of the object, and also the fragments that build this object. This comes from the studies from Spelk. So how we can like make sense of some surfaces and assign an object for a set of surfaces. So events are represented by vectors. I'm not going to explain all of it, but the idea is that every time as an object is moving or changing any kind of property, let me show here. Oh no, I'm going backwards. Here, we have events that are being detected online. So we have these vector representations being updated for every time step, which is not very efficient, but it's how we do it right now. And then we have episodes, which are like the relationship between events. So the idea is that event representation is enhanced, and we give like the relationship between these events and other events using Allen's temporal logic. So we try to see which events have like some spatial and also time contiguity, and we can track like, oh, if this event has just finished and another one has started, and the objects are pretty close, by studies from Michaud, we can say that maybe this has some kind of causal relationship. So this is the way that we are doing.
Thank you.
Here, for the cultural relationship between variables, have you explored or given a thought about transfer entropy as a mean of measuring causality?
Like, I didn't understand so well. What do you mean by entropy? Like entropy,
transfer entropy. Well, in information theory, that's what we use actually to. It's not just the timing when something happens, but you can actually measure the entropy and see the transfer between one variable and the other.
Oh, this actually makes a lot of sense. I didn't thought about this actually.
Yeah,
but
well, there's a lot of papers on that.
Oh, that's very interesting. Yeah. Because I'm aware of information theory, but I never thought that we could use like for detecting causality. So it's very interesting.
Okay.
Thank you.
Well, thank you so much, Yuji. That's a great presentation. So congratulations.
Thank you.
So let's continue with our next presentation. And the next speaker is Mario Enrique Osuna.
Can I start now? It's working. Okay, thank you for accepting this talk in this BICA conference. So I have to say that this is not actually my work. This is the work of a PhD student, Sergio Castellanos, and he couldn't be here, so I'm taking his place to. So I will explain as much as I know of his work. His work's titled Systematic Guidance for Extending the Appraisal Process in Computational Models of Emotion. Not sure if it's working. Okay, thank you. So first of all, I will try to provide a background of his work, that is the role of emotion in the context of artificial intelligence. So as you know, and as we can see with other works, cognitive task has been remarkable advances in many cognitive processes. For example, decision-making, attention, and memory, learning, and many other cognitive processes. But for this work, we focus on a particular cognitive process, that is emotion. And a core aspect of human-like intelligence remains a challenge, that is the ability to perceive and adaptively respond to human emotions. So enhancing emotional understanding is crucial for creating more natural, intuitive, and human-centered interactions in AI systems. So the main idea is to improve the human-computer interactions in many fields involving with agents that are capable of express and simulate the human emotions. And well, the emotion is addressed in the literature what we call computational models of emotion, that are software systems that attempt to imitate some of the process of human emotion. And most of the models that are reportedly in literature have three phases. The first phase is about the evaluation. That could be a cognitive evaluation or physiological evaluation. And then there is, after this evaluation, there is an affective state derivation. And after that, there is an emotional response. So for the purpose of this work, we focus on the first phase, that is the evaluation. And as I said, there is two kinds of evaluation, right? And we even focus in cognitive evaluation, that is more complex and involves the calculation of what we call appraisal variables. So as been said in literature, that these cognitive evaluations have this what we call influencing factors. Influencing factors are the internal and external elements that modulate our appraisal of a given situation. And for example, of this influencing factor could be personality, social culture, norms, social context, and many other things. So the result is a significant variability in emotional response to the same event. That makes that these influencing factors determine or shape the way in we evaluate a specific stimuli. In the work, we create this taxonomy to categorize in these different types of influencing factors. And we create those influencing factors that have to do with personal, with contextual, with social, with cultural, and with situational elements. And in the paper, we briefly describe how each of these categories can affect the process of appraisal. So the problem that we are addressing in this work is related to computational models of emotion, and particularly with his model of appraisal. When we reviewed the literature, we identified three core issues that was interested for us. That is incomplete coverage. That means that most models produce oversimplified emotion because they omit many relevant EFs like personality, social knowledge, or past experience. Most of the models currently integrate one or two influencing factors, and they do this internally in the model. So it's difficult, and this leads us to the second issue that we identified, that is ad hoc integration of new influencing factors. When influencing factors are included, they are typically implemented using ad hoc strategies, and include new ones makes it very difficult for a given model. And the third issue that we are focusing is in the lack of standardization, because there is we don't find many information about these influencing factors and how to integrate in models. So this lack of sharing methodology for integrating influencing factor, which obstructs the comparison of results and slows the accumulation of knowledge. And to address these three key problems, we propose what we call ACME, that is an appraisal-based computational model of emotion, influencing factor systematic giddleness. So the main idea, what I will explain better these 3 points. What it is? Well, it's a formal step-by-step procedure for conceptualizing, grounding, and integrating influencing factors. And the main idea is to provide a procedure to take or develop a new influencing factor and integrate it into a current developed computational model of emotion. So to create this systematic approach, we structure it as two main phases. So these two main phases leads to the integration of a new influencing factors, where each of these phases have 2 stages, and every of the stages has several activities that can be taken as a guidance to integrate a new influencing factor. So this is a high-level overview of the proposal. That is, as I said, 2 phases. The phase 1 is about building influencing factor. The phase 2 is more related to connect the already development influencing factor with a current computational model of emotion. And at the red side, we have one of the activities that we identify as important to do in order to achieve the goals of the outputs that we describe for each one of the phases. So I will explain mostly the goal of every element, for example, the phases, and then the goal of each of every stage, as well as key activities that we define and the output that we can expect. So the phase 1, the goal is to move from an abstract concept to a rigorous defining an executable influencing factor component. And this is addressing one of the 3 key issues that we identify starting the presentation, that is incomplete coverage of influencing factor in the current models, or at least this is what we expect to impact. The first phase have this first stage, that is analysis and specification of the influencing factor, and has as an object to produce a self-contained or generate this what we call influencing factor profile, and have some of the activities involved in this stage is the selection of a target influencing factor, the selection, analyze the model of emotion that will act as a host or interact with this influencing factor, conduct a literature review, and formally specify of influencing factor scope, boundaries, and its mapping to appraisal variables, because these influencing factors are materialized in the appraisal variables or shaping the value of these appraisal variables. As an output, we expect a comprehensive influencing factor profile document that includes basically the result of each of one of the key activities that we identify. So the stage 2 is related to develop the influencing factor component, and has as an objective to design, implement, and verify this influencing factor has a standalone software system. In place, the activities has create a technical design, code the component, and perform unit test. And this test has to do with the technical part of the influencing factor as a software model, and not yet has a theoretical integration with the model. And as an output, we expect a function validator, well, a functional influencing factor has a standalone software. So the phase 2 is about to, once we have this influencing factor already development, the main idea is to connecting with a computational model of emotion already development. So the goal is to integrate the influencing factor model into a model of emotion workflow via standardized contract, addressing ad hoc integration of and lack of standardization that we previously identified in literature as a issue. So the stage 3 is about to modulator design and the integration, and has as an object to embed the influencing factor model into a computational model of emotion, and specify these technical contracts at software level, and involves key activities as defined integration strategy, implement technical connections, for example, using design patterns and interfaces, depending of the language, the programming language that is used. And we expect as an output an extended ACME with the EF active and an integration report of this technical description. The stage 4 is the integration and compatibility validation. And the objective is to validate the integration and now as a theoretical level, not just to technical, trying to prove that the integration produce values and these values make sense in the context of the model of emotion, and implies key activities as the plan validation scenarios or case studies, execute these cases studies and analyze the data resulting, and just tailor parameters if is needed. So the output is a calibrated, stable model of emotion with the influencing factor already integrated. As you can see, this is just a first step of the project. So we don't have a formal validation yet. The PhD candidate is working already in a more formal validation, but for the publication in the conference, we provide a proof of concept. And basically, we take every one of the activities, stages, and phases, and trying to integrate an influencing factor. In this case, it was cognitive fatigue, and try to define the decisions that we take in each of one of the activities in order to at least at conceptual level, integrate it into a current model of emotion. So our proof of concept focused on validate 3 key attributes that we name it conceptual formalization, that is the ability to transform an abstract idea into a detailed operational and testable definition, and to make this documentally traceability, because there is not that much guileless or procedures formalizing in literature, so it's basically like walking in blind when we try to do something with models of emotion. So we try to impact that part, making this systematic guileless and creating formal documents to other researchers to take it and see how it can apply in individual contexts. And the third part of the attributes is the experimental reproducibility. That means that the delivery of a self-contained technical package can allow us to exact replication of the experiment. We define how these 3 elements that we believe the systematic guilelessness provide impact on each of the problems that we underline in the start of the presentation. That is incompleteness coverage, the conceptual formalization in practice provides a structural template for specifying new EFs and directly combining incomplete coverage, because the idea is to integrate new influencing factors. So the models are not limited just to internal influencing factors, but can add new ones. The documentality traceability, as I said before, the main idea is in every stage create a formal document as an output that can be used as a documentary traceability. And experimental reproducibility is supplies a charted executive package promoting compatible experiments and addressing the lack of standardizations. And the systematic idleness naturally impact the lack of standardization in literature when we try to build this kind of models. And well, this is more of the same that I already mentioned. So thanks for your attention, and this is the first step of this project.
Congratulations, Mario. Nice presentations. Any questions?
At several points in your presentation, you mentioned test some of these things and also validation. I'm just wondering, what do you propose? How do you propose to test and validate those constructs? And also a related question is in many existing models of emotion and appraisal, they used, if I remember correctly, 4 dimensions. Of course, each dimension involve a number of factors. And do you have any comparisons between your system and those existing systems in terms of their performance improvements and things like that?
Okay, thank you for your question. Your first question is related to how will be a formal validation, right? So we already have a model of emotion in the lab, and we are working that is infra, integrative framework. It's already published computational model of emotion. And the idea is to define, following the steps that we define and the activities, create a new influencing factor and integrate it into the current model that we have. So, of course, we need to define the case study and what we will present as a numerical validation for that integration. But that's the main idea at the moment, using the model that we already have and create a new influencing factor as a total different and third-party development and integrating. And your second question was about current models in literature, right? And I don't understand what you mean, because currently models have uses appraisal variables to calculate the cognitive evaluation. So these appraisal variables eventually evolve in an affective states. And the role of influencing factor with these appraisal variables is that the way in which the models calculate these appraisal variables is based on influencing factors that they integrate into the model. For example, personality or the goal, the agent's goal. So, for example, you can define several goals internally in the model, and for calculate appraisal variable, name it goal conductiveness, you just check how this stimuli impact in the goals that are already in the memory of the model. But these kind of models are not including more influencing factor, and we know by theory that more than the goals and several elements like personality, cultural norms, and other things shape the way in we realize this cognitive evaluation. So the main idea is to extend the number of influencing factors that we can integrate into a model of emotion in order to calculate more precisely appraisal variables.
Any other questions?
Thank you. So if I understand correctly, so you're trying to keep this really general and abstract so you can kind of plug in new influencing factors to your model of emotions as you go. Kind of going into it, you don't really know what those factors might be, but whatever those things might be, you want to be able to make it as easy as possible to integrate those factors. Do you have any concerns that because it is so general, that the style of integration, how it influences your appraisal system, might be radically different depending upon whether it is some particular cultural or social factor, something that might modulate attention and, by extension, then affect emotion? Or do you have any concerns about, just because it is so abstract, that you might have a difficult time doing all of these different factors in exactly the same kind of way?
Yes, actually, the main idea of this kind of guidance comes from software engineering. That is a big field where a lot of procedures and formal methodologies are standardizing and function very well when you try to develop a new software system. And that the idea came from that, generate standardized methodologies. But when you try to match with the problems that we have in cognitive processes, a lot of things doesn't work. So that was the first problem that we find, and most of the activities that we propose are just an abstract level, in letting the researcher to take that decisions and how a particular influencing factor will affect a specific appraisal variables. And we can say how, because each model of emotion is particularly, but we identify the activities that the researcher must to do. For example, defining in which degree will be the effect and in which appraisal variables will be. So that kind of decisions, we formalize it and try to provide it to the researchers and leading them these big decisions.
Okay, so it's like a magnitude of the effect and directionality for negative, positive. What is is there one common interface in terms of, like, if you think of like a mathematical equation, each factor is a positive valence versus negative valence? What is the essence of the thing that combines?
Yeah, the equations used must be defined by the researchers, because that was one of the problems that we find. We start with a big proposal, but with several decisions already made for the researcher, and part of the work was just throw with them and left just the ones that leaves the decision and activities open to the integration. That is the work right now, and we'll take your recommendations for future steps.
Thank you.
Thank you.
Well, no more questions, so thank you so much, Mario. Congratulations.
I appreciate it.
So the next talk will be presented by the Dr. Andrew Knoxall.
It's third day. It's late in the afternoon. I will try not to lull you to sleep. Nope. Oh, wait. That worked. Okay, a presentation in 4 parts. The first one will probably be a review for a lot of you. So, psychology, the consensus is that we have arguably 3 different types of long-term memory, and one of them is episodic memory. So, where did you park your car this morning? What did you have for breakfast? When was the last time you were on an airplane? There's some argument that there's two different kinds of episodic memory. We're not going to go there. So compared to short-term memory. So just to contrast, if you're new to this, a semantic memory is your knowledge of facts. Who was president before Donald Trump in the United States? You probably don't remember where you learned that, but you know the answer, right? What color is a ripe banana? That's semantic memory. Procedural memory is your knowledge of, sometimes called motor memory, how to do things, how to walk, how to talk, how to juggle, how to ride a bicycle. Everyone knows how to juggle, yeah. If you don't have a fully functional episodic memory, if it's impaired, the word we use for that is amnesia. And there's some pretty strong evidence that a human with impaired episodic memory can't learn very quickly. So it seems very important to learning. As a previous presenter mentioned, there are a lot of cognitive capabilities that seem to be associated with episodic memory. A couple examples: virtual sensing, retroactive learning. For example, if I ask you where you parked your car this morning, you might imagine yourself walking from the parking lot to the university. I don't know, maybe everyone walked or took a taxi, but you can relive a scenario, and that can be very useful. Implication, I can't prove this, but I think it's a really important part of cognition, and if we want to build an artificial general intelligence. So to that end, I do a lot of work with something I call the blind finite state machine environment. I'm going to hope everyone here knows what a finite state machine is, but I bet you can guess even if you don't know. I'm randomly generating finite state machines with a given size, as in given number of states, and a given number of actions in each state. So this particular one has 4 possible actions in each state, A, B, C, and D, for example. But you could have more or less or fewer. And it only has one goal state that can always be reached. So, whoops, I went up a slide, didn't I? One goal state that's always reachable. So if you reach the goal, you go to a new state immediately. So why would I do this? Stay with me. I make it blind by giving the agent as little information as possible. The agent knows what actions are valid. It knows if it's reached a goal as a result of the last action, but it has no idea any other information. And this seems like a really simple problem, but when you remove all this data and give the agent as little information as possible, it becomes very difficult. And that's because it essentially are creating extreme perceptual aliasing. So if you don't know that term, the idea is that there are multiple states that all appear identical to the agent. You could do this to a human by putting them in a maze where all the walls feel the same and there's no lights. Can you imagine that different moments in time might feel very similar to each other? That's essentially what we're doing to the agent. So if we take out of the box TensorFlow, artificial neural network, and put it in blind FSM, it does terribly. And that shouldn't be surprising because it doesn't know where it is. A lot of machine learning algorithms require some distinction between states. And there's some work, partially observable Markov decision problems and these types of things. Certainly there's some work in this regard, but in this particular case, I've set it up. And that's on purpose because this is an environment where episodic memory is essential. If you can remember sequences of actions that you've taken, that might help you get out of this dark maze. So, and that's what we wanted to do. So we take the artificial neural network and we add a really rudimentary episodic memory. So in this particular example, and we did multiple different blind FSMs, but in this one, the alphabet size is 2. You can only do A or B from any given state. And if you do an action, you may or may not reach the goal as a result. So if I underline a letter, that means the agent reached the goal as a result of taking that action. Okay? So essentially there are 4 possible episodes for this agent, really small number of episodes. And what I'm going to do is I'm going to take the recent past and I'm going to plug it in along with, actually the B is a action that the agent wants to do. and I turned that into a binary representation. I put it in the neural network, and it gives me a guess: A with a goal, B with a goal, about how likely it is that these will occur. And then I just use a softmax to turn it into a probability, or sort of a guess probability. And so I'm going to show you how the spoiler, as I said, is that this does work. I'll show you some results in a sec, but this is the baseline agent that we use to do this research. And this was the hard part, was building this guy. So once we had it working, we tried to improve it. So the paper talks about some of the approaches. One of them is that TensorFlow has a built-in tensor called a long short-term memory that is designed to sort of remember past events. And so we thought, well, we'll put this in here and see how it does. And then we also began looking at some epsilon greedy-like strategies. If you don't know epsilon greedy, I think a lot of you do. The idea is that when you're first starting out in an environment, you don't know what decisions are good, and so relying on your knowledge is probably not worthwhile. But as you gain more and more knowledge, you want to rely on it more. So it's explore versus exploit. So traditionally what you do is you start with a variable, and you can tell when people get excited, they start using Greek letters. So they called it epsilon. And they said when epsilon is really high, then there's a high probability that we will take a random action, and then over time it decays down, never quite reaching zero. And that works. That can work very well. But one of our goals in this research was not to be environmentally dependent, because it has to be tuned for each one. So we began thinking about ways we could make a self-tuning epsilon, an epsilon that might actually go up and down over time. And we had some really cool results from this. So we began with what I now call a global E-greedy. We looked at the last n trips to the goal, and we experimented with different n's, but it didn't seem to matter very much as long as it was reasonable. The last n trips to the goal, and compared that at average steps to reach the goal compared to its lifetime. So you had some idea of how well it's been doing recently. And that might help you understand if you're making the right inferences about what's going on. But we later discovered that we also need to look at specifically at the current run to the goal, because you can imagine when you're so confused, it would be really easy to get in a loop. Even you in a dark maze, if there was a circle somewhere, you might find yourself in it. Or a person in a forest, right? They commonly go in circles. And so if you're saying, gosh, it's been a really long time and I haven't reached the goal yet on this particular attempt, that's not good. So we made a local E-greedy to measure that. And when we multiply these two epsilons together and use that as our actual epsilon, we got some, in some cases, the best results. So let's look at those results. So here's a really small blind finite state machine. Only 10 states, only A and B for actions. And what you're seeing here is on the x-axis, we're making successive trips to the goal state. So, when you start out in the first trip to the goal state, you have no knowledge at all. Your episodic memory is empty, you're a blank slate. And as time goes on, your multiple trips to the goal, you gain more experiences that you can draw upon. So, and then at each of those, we did an average steps to goal. And this is a smoothed average. We did multiple runs in order to see these patterns better. So there's a lot on here. Let's start with this vertical line here. There's more detail in the paper, but that's called the model creation threshold. Essentially, that's the point at which we decided we had enough knowledge to actually try to learn from it. So anything before that horizontal line is a little bit more suspect. I don't know. And then I remember I talked about our baseline. Unfortunately, we called it benchmark here, but it's the same one. It's this baseline architecture that I showed you at the top. That's that guy right here. Oh, I should show you this one too. This horizontal thick orange line is labeled as optimal. You can't ever be optimal in this environment. Even if you knew everything, you knew how many states there were, well, not everything, but if you knew how many states there were and you knew what the transition table was for the finite state machine, it's still impossible to behave optimally because you don't know what state you're in. So you can only make a best guess. So this optimal is based upon knowing everything, which is impossible because in blind FSM you don't. But it provides a good sort of reference point for understanding the data. So, so we have the benchmark performance. This is with the long short-term memory tensor. And then we use just global epsilon, and then we use the product of the two. Now for this FSM, they're all about the same. And they're all performing well, right? They're all performing significantly better than random. Here's a bigger one, 20 states, 5 actions. Now we're seeing some variability, and we can begin to sort of separate these out. One of the things that's really interesting is the long short-term memory is the slowest to learn, but arguably this is the best. It's not statistically better, but it looks good. And then here's a bigger one. Here's the biggest one we did. It's kind of expensive to do this, so we only did 3, but we were trying to show that it could work with multiple different environments. And so again, you can see long short-term memory in the benchmark. Without the epsilon, it takes longer to learn, which I guess isn't surprising in retrospect, but it's something we had to figure out. But in the end, they were able to achieve the best performance, but the best overall, in my mind, is the global times local, where it learns faster and performs as well. That's interesting to see. So sort of a metacognition and awareness of how you're doing can be really powerful too. I thought that was interesting. So I think that's the last slide. Oh, well, future. I've never used the deep Q learning architectures. There's a couple out there. I have some students who want to tackle that this fall. And if anybody has experience and can make a recommendation about how to get that set up, I'd love to talk to you. But we want to give it a shot. And then one of the things I think episodic memory can be really useful for is noticing when the environment changes. So I really want to go there as well. So, all right, thank you.
Very interesting, Dr. Andrew. Any questions?
I was wondering if you have a thought about using a transformer for that, because it seems to me that a transformer might give you something very similar to what an episodic memory can provide you.
So I have a colleague who suggested that, and we actually went about building a custom transformer, and something went wrong, and I forgot. But there was a problem with it.
Okay.
But we kind of designed one and coded one up. So yeah, that doesn't mean it wouldn't work. We got stuck. Not maybe a satisfying answer, but okay. We did try.
Thank you.
Thank you very much. I appreciate it. Really enjoyed it. I was curious. So right now you have deterministic state transitions in your blind finite state machine. Have you experimented at all with some probabilistic transitions to see what that, so change over like a Markov chain kind of environment?
I have in some past research, but not with this particular architecture. I'm trying to remember what our results were. I think what we saw was that it was pretty comparable, as long as it was reasonable. You know, if your odds of a random transition are 80%, then it kind of goes nuts. But
Right.
yeah, it was pretty.
It's an interesting other source of noise. It's like
yeah.
Completely blind that's a hard problem. No doubt about it. Like everything is just a state alias, and sort of figuring out like, okay, well, you've got some state aliasing and then maybe some noise related to, not deterministic. Be interesting to see some of that stuff. The other thing is I've used stable baselines 3. So if you want to do DQN stuff or other stable baselines 3, so we can talk more about it, but that might be a way to get some off-the-shelf deep Q learning.
Oh, nice.
Yeah, so please.
Yeah, I welcome. I saw in your talk that you've done some work with that.
Yeah.
I would love to hear your advice. I don't have lots of money to buy my own machines or rent things, so rent space on Google's servers. So
yeah, we can talk more about it, but yeah, I can try to. Yeah, thanks. Great.
Una más?
Very nice presentation. I have a question. Like, when you're sampling like random finite automata, are you assessing like the complexity of them? Like, because there are some that are easier and other ones that are harder.
Yeah, it's true. Yeah. So Eduardo makes a really good point. A random finite state machine can be really easy and really hard. And I've done a lot of looking at sort of what makes it hard. It's actually really fascinating. But what I have found is that if you do enough machines, it averages out. But definitely that's why it's hard to get statistically significant results, because there's so much variability. We could generate, in fact, we do generate the same. I seed the random number generator, so every time we run it, we get the same machines. Every time we run the experiment, but the agent doesn't know that they're not truly random.
Nice. We can talk later, but what you can do is using LZW or some kind of compression based, for example, trying to approximate Kolmogorov complexity, and then you can have like estimate of which machines are harder than the other ones.
That is a cool idea. Absolutely, that's a good idea.
Another, you said before, like you were searching for some kind of module that can use deep learning. I would recommend neural episodic control from DeepMind. So different from the transformer, it relies in episodic memory, tries to simulate episodic memory. I have some criticism over it, but it is more this persistent memory, different from what we have in transformer-based architectures that are mostly based like in the number of frequencies of time. The architecture will see this in a stochastic process, but there's no persistency. So
I want to start with something that just does deep Q learning without an episodic memory, because then I want to see the difference when you add it. So that's important.
Yeah.
But yeah, it sounds good.
Okay, we can talk later. I have some implementations DQN.
Am I going over time here?
Hi, Andrew. Thank you for your presentation. I have only a question. For example, how would your proposal determine the final state?
How would I propose?
Determine or understand when the final state? Final state.
Like, how do you propose doing what in the final state?
Yes, and your proposal consider when, well, we can have more one final state.
Or more than one final state?
Yes.
You know, I've never tried it, but my intuition is that it wouldn't make any difference, that the agent would sort of learn that if I feel like I'm in this part of the FSM, try to get to this goal, otherwise, and it might not even be aware that there's multiple goals in that case. But maybe you're right. Maybe there's more to it than that. But I have to admit, I've only tried it once and it didn't seem to make a difference.
Okay, thank you.
Any more questions?
Thank you so much, Dr. Andrew. What a great material. Well, our next presentation will be performed by Ricardo Talavera.
Thank you.
Hello, everyone. My name is Ricardo, and I will talk about intervention in complex systems with self-organized criticality through deep Q learning and case study in vehicular traffic. Okay, it seems it doesn't work. Okay, before start talking, I'd like to talk about the definition of complex systems. In brief words, it's a set of elements with interactions generates not predictable or emergent behaviors. In past sessions with other speakers, we have talked about this, no? So it's new. But the more important thing about complex systems is its characteristics, no? What defines a complex system in terms of the characteristics? And there are two main characteristics that in every complex systems exist. There's emergence and self-organization. Yeah. In emergence is how a new property arises from the integration of the parts that compose the systems. No? For example, if we talk about the muscle of the body, one only muscle have a very simple behavior, but the integration of them is a runner in a marathon. So that behavior is not expected and is an emergent behavior. The emergence talk about different scales from macroscopic and microscopic, but the self-organization talk about the time, how each element interact and form the patterns or structures in the time. Another property that is very strong or very important to this work is self-organized criticality. In a few words, is how those elements makes that the systems reach a critical state. This state is metastable. So only one interaction, very simple interaction, could make a phase transitions and the microscopic properties change. An example of phase transition is this. We have ice, and after the phase transitions is water. If this is not a complex systems with self-organized criticality, it's a good example to understand what is phase transition. The most important or the prime example of self-organized criticality is a pile of sand, where each component is stacking, reach its critical states, and then collapse. This collapse have two properties. That one is 1/f noise or pink noise, and it talks about the size of the event. That means that lower size events is more frequent than the largest one. For example, earthquakes. Every day, earthquakes happens around the world, but at different magnitude. The similar structure, the most important or most known one is the Sierpinski triangles. That means that the structure has smaller copies inside the main structure. Okay, a question could be arise from this presentation, that is possible to intervene a complex system with self-organized criticality? Well, in some scenarios that couldn't happen, sorry, for in example of earthquakes, but there are other systems that could happen. Some of them are biological, and others such as traffic congestion, massive blackouts, and incendiary forest. In the state of art, was a systematic review that was done following Prisma methodology. The workers used with complex system and intervention. The inclusion criteria was taking account self-organized criticality and the use of technology as intervention elements. And the exclusion criteria is specific fields such as health and psychology, because we want to address from a more general point of view. This was the database used. We started with this number of articles, and after all the filters, we have only 3 important articles that matters with the subject. The first one talks about networks. When each node of the networks are autonomous and independent and has a load, when the load is near from the critical state, we disconnect that node from the networks so that the collapse in a local sense. In this graph that has been shown before, the event size of the distribution is like this. But once we disconnect to prevent a systematic collapse, we should expect that the shorter event size will be more frequent, and the systematic failures will be even rarer than actually are from the beginning. And here. Other study talk about the uses of shield agents that seek for others agents in the systems, found the most disaligned from the desired heating or position, and try to fix it from an actual heating to the desired heating. And the next one is the prime example of the organized criticality that are sandspine models that was in the previous works. We localize the smaller collapses. The probabilities of a smaller avalanche are calculated, and when they are near for a critical state, we collapse them locally. And also we expect that the distribution change to avoid systematic collapses. In this framework, we use DQN for make intervention in complex systems with self-organized criticality. The intertraining method, we use experience replay, target network, and epsilon greedy. one way to understand in a few words what actually we're doing is that environments had a lot of characteristics, such as the high dimensionality, self-organization, emergence, and others. Then one agent get that observation from this environment using IoT sensors, and then in a network communicates with its local behaviors. Then concatenate information, preprocessed information is needed, and then processed through the DQN, and an action is selected and is used to intervene the environment. Here, before we pass this information to the DQN, the most important is this parameter. This parameter is a control variable to decide how we intervene in the complex system, if we want a phase transition or not. And then we use, for the training, the epsilon greedy method where I talked before. In the reward function, we have to take into account some variables. The system impact variables that depends of the proper systems. For example, in traffic vehicular is density. In the balance of states or taking actions, we need to take incur this reward because in some cases it produces deadlocks or starvation. So if we want to avoid that, we need to consider this in the reward systems. And also to avoid rapid state switching, a reward of keep being in the actual state is needed. In the case study, we use traffic vehicular because traffic vehicular is a complex system with self-organized criticality. And the most important variable here is density. It's not the speed, it's not the amount of vehicles, it's density. In other works, they used artificial intelligence and the QN for vehicular traffic, but their point of view don't consider complex system perspective and use variables that does not follow the complex systems with self-organized criticality, and those solutions don't correspond to the root of the problem of traffic. And the other is that the state of art in vehicular traffic don't consider more realistic scenarios. Most of them only consider one intersection. So the question is, how will they solution a problem like that? Only consider our ideal scenario. It doesn't make sense. The environment in this case study was a wall neighborhood. In this, we will control the traffic lights as interventions for this environment. Following the equation that's shown before, and the simulation. It will be done using GAMP platform for the needed tools for the simulation, Python for the QN, and the communication between the two platforms were with REST API. The simulation will start with 800 vehicles driving randomly, and we try to control the traffic lights and reduce the density to avoid the phase transitions and avoid congestion. To measure the effectiveness of the proposal, we take two policies. That the one is the traffic light control system that is working in almost every city in the world, that is schedules, times, states. And the second one is the intelligence policy of this proposal. The metrics compared is meaning time per vehicle, average speed by vehicle, and performance by density. And this is important because if vehicular traffic is a complex system with self-organized criticality, then we must see how those metrics works with different density scales, because the density is the main root of vehicular traffic. The reward system was to reduce the low density, to balance the number of states to avoid deadlocks or starvation. because think about it, in a world with all traffic signs, where only green. So to avoid that, we take on care of local balance of states. The duration of the present, because we want to rapid switching between the states of the traffic signs, and the reward is only the sum of those. And the results, it was the intelligent positive was better than the traditional one. For example, the blue line is the traditional one, and the orange one is the proposal. In the proposal, 68 vehicles have passed from this intersection. That means we count how many vehicles pass the intersection from the beginning, for the last one, to it was the traffic light. And in contrast with the conventional time policy was 34, almost a double. In the mean velocity, the proposed policy was 67% better. And finally, in the average waiting time was from 24 seconds of the time policy, traditional policy, to the 11 seconds in the proposal. And that's it.
Great work, Ricardo. Very interesting. Yes, we have.
Well, congratulations, very interesting. I would like to know which information you're going giving as input to the QN.
Oh, okay. The information were three types of information.
Okay.
First of all, it's important to say that the information to the model was not only to local for one traffic sign, was for a local neighborhood. So each variable was also the same variable for the local neighborhood. I used three that was the density of the street they were controlling. The second one is the state that is the traffic sign in that moment, and also the time that has been in that state.
Oh, very interesting. It's very interesting how you can only use this data to converge. So congratulations.
I didn't understand your question. Could you repeat it, please?
Sorry? No, I'm only giving like congratulations. Like
okay. Sorry.
It's very hard to make it work only with like density.
Yes, it could be think about in that form, but I think we could be biased because we could think that by more information we have, more possibility to address a problem could be, but it doesn't be the case depending of the problem. No, has been shown in the field of complex systems that only one variables impact the phase transition in self-organized criticality, and also because we are in BICA, it has impact in some fields that are inside of the biological inspired cognitive architectures, such as the brain, consciousness, neuroplasticity. So it's important to keep doing research in self-organized criticality.
No? Okay. Thank you, Ricardo.
What a wonderful work, Ricardo. Thank you so much. So according to the schedule, we have our next presentation that will be performed by Bradley Alicea. So Bradley, are you ready?
Yes, let me share my screen. All right. And hello, my name is Dr. Bradley Alicea, and together with Morgan Huff, I'm presenting the augmentation of intelligent agents for human-machine superperformance. We're both affiliated with the Orthogonal Research and Education Lab. So when we talk about human-machine superperformance, we're really talking about these symbiotic systems that involve a combination of human intelligence and machine intelligence. So when humans and machines work together, they can leverage complementary strengths. And again, this is something called human-machine symbiosis. So if we go back to 1957, Herbert Simon made the prediction that in 10 years, a computer will be able to beat a grandmaster chess player. Well, it took a little bit longer than 10 years, but in 1996 that finally happened, and Garry Kasparov was defeated by Deep Blue. So what happened after that was the development of something called centaur chess, where supercomputers and humans leveraged their relative strengths to build a better chess game. So in this paper we reference something called a world model. This is an evolving area, so these points are very general. A world model should provide a conceptual framework, a representation that helps a computational model interpret incoming instances from the environment. The second is that a world model should build a compact state-space representation based on sensory inputs. A world model should predict the consequences of potential actions. A world model takes a high-dimensional and stochastic sensory signal and reduces it to a compact representation. And then point 5 is that world models are a model of all plausible simulation scenarios. Basically, the first 2 or 3 points are what typical neural networks or deep learning models do. And then 4 or 5 additional models, such as reinforcement learning or a symbolic model. So the first example I'll show here is this paper, World Models by Hahn, Schmidt-Huber, and this was published back in 2018. The machine tries to not only take the inputs and produce outputs, but it takes inputs, it builds a world model, or a model of all possible states of the simulation, and operates from that. So in this instance, it's trying to drive a car around a racetrack, and to do this, it builds a compact planning representation. Sensory sampling is a predictive model from a probability distributions. What you find in this example is that planning and sampling are balanced, and that balance comes through a generative. We need to do some planning, but also some sampling from the environment to make sure that it's on the right track. Now, we talked about planning and sampling in our paper from 2023. We can also define super planners and super samplers. Those are those individuals that have a high degree of planning or high degree of sampling. In this relativistic regime, you get high planning and high sampling, and that's what we'll be talking about with respect to our human-machine superperformance. This is where we have a pursuit evasion model, and we're looking at the coevolution of agents where one has a high degree of planning, one has a high degree of sampling. Paper is called World Models in Artificial Intelligence, Sensing, Learning, and Reasoning Like a Child. They propose a world model where you have humans in the loop that update the model. You have a physics-informed modeling, which is also embodied. You use a neurosymbolic component, you use causal inference, and you have this open-ended machine learning model. So you have a training set, and that training set is interpreted by the world model, and that provides a higher level of awareness or intelligence. Another thing that we talk about in our paper is this idea of the flatland problem. There's a book from the 19th century called Flatland, A Romance in Many Dimensions by Edward Abbott. He provides this thought experiment, creatures that live in a one-dimensional or two-dimensional world, and they're interacting with a three-dimensional world. So the idea is that those creatures can't conceive of a third dimension, and that third dimension disappears. It's relative to the viewpoint of the agent. The flatland problem is a problem of low dimensionality. There's a lack of dimensionality, and it impedes the ability of that model, or that internal model in this case, to understand the full picture. And so this leads us to this idea, the world always having a higher dimensionality than the model. So the model usually doesn't have as high a dimensionality as the world. And indeed, in machine learning models, we usually do a lot of dimensionality reduction. Machines often don't capture the full dimensionality of the real world through their inputs. So in the paper, we introduce a number of variables. The first is that of the sensorium, which is this from a paper we've done on something called Gibsonian information. And this is describing the dynamic experience with an agent's sensory world. So an agent interacts with its sensory world, and it extracts these parameters, which are then calculated into the sensorium parameter. So we have what we call coherent movement. So in the environment, there's usually some sort of coherent movement against a background or amongst particles or something like that. And then we have information decay, so that coherent movement decays, maybe masked by noise. Then there's an internal experience of coherent movement. So internally, the agent interprets the coherent movement through their sensory apparatus, and it's represented or it's sort of processed in a way that's different than the coherent movement. And so that's divided. We take the internal experience of coherent movement from the coherent movement, and then we subtract sensory delay, which are the delays in getting information, which serves sort of as another aspect of decay or another dimension of decay. We also have this issue of the ecological psychology of the sensorium. So the sensorium is important because in the world we have all these things that are moving around us constantly. And as an agent, you have a world model that represents these points. It represents the motion of these points, and then it represents these different parameters of the relation between the intelligent agent and objects in the world. And so this shows kind of that relationship. Then we have these sensory modality specific gradients. So we have the sensorium, but then we have these gradients through each sense. And so an agent can have multiple senses, and multiple senses, in fact, are needed to build a world model, to build an intelligent system. Each sensory modality, source of input, forms an input vector. The input vector is represented, the nabla describes the gradient, which is sort of the direction of change. So you go from these vectors to these gradients, and then you go to an angular displacement between those vectors. So you look at the difference in how these gradients are being explored by each sensory modality. And so this is kind of an example of the exploration of this gradient. It's a two-dimensional gradient, and then there's this path that goes down the gradient. So we define intelligence as a function of multisensory and 4D spatial worlds. So we have 3 dimensions of space, 1 dimension of time. And this is the representation here, which is I. And I stands for intelligence. And in this case, it's the difference between generativity and selectivity. A couple of notes here. Low degrees of generativity are penalized relative to both low and high degrees of selectivity. And super performance, as we've defined it, maximizes both generativity and selectivity. In those cases, intelligence is amplified. So we have generativity and selectivity. So generativity opens up the number of possibilities, whereas selectivity selects the most optimal, interesting possibilities. And so you need both of them maximized to really get a high level of intelligence. And so we have a couple of cases where we play around with different values for both G and S, and we end up with different values for intelligence. And we find that generativity is important, but so is selection or selectivity. So here is our figure for both the intelligent agent and the world model correspondence. The interesting thing to note here is that each of these intelligent agent and world model have a set of discrete states. This operates according to a state-space model. So the state-space model has to correspond. So in other words, the same or similar number of states in both the intelligent agent and the world model are considered well-regulated or well-controlled. Whereas if there are more states or many more states in either one, then it's poorly controlled or poorly regulated. And so this is an example. If we use Shannon information, we can see that in this case, the world model has a much higher level of Shannon information than the intelligent agent. And so we ask the question, how well does the state space in A match the state space in B? And so if A and B are ill-matching, there's this anti-aliasing process that goes on. And so, we might ask, in that case, if we go from one state in A, we can map to multiple states in B. And so it's hard to know which state to map to. We also can't really determine how feedback should occur. So if we get feedback from one of the smaller, more specific states in B, that maps to the more general state in A, but it's hard to know what for A to interpret that feedback. And then, of course, if we have closed loop positive feedback, if we have more and more states in A, then it's easier to map or correspond to the actual phenomena in B and vice versa. And so this leads us to some interesting questions in intelligence augmentation and distinguishing that from artificial intelligence. So instead of using data and algorithms to simulate human intelligence, intelligence augmentation uses data and algorithms to work with or complement human intelligence. So this is the natural intelligence amplifier as defined by Ashby. You have a regulator X in a system S. You have an intelligence measure G, which is what the regulator is sending to the system to act upon the system. And then there's this corrective signal or feedback in you that improves the performance of the regulator. So if the regulator is maybe it's like a person operating in the world, being able to do things in the world competently, walk through a building, navigate through a building, read a map, things like that. And then if they make a mistake, there's a corrective signal or feedback to help them improve their performance. Now what we're proposing here is a super performance enhanced intelligence augmentation. Using a similar model as we have to Ashby, except that we have a couple of differences in both the feed forward and feedback components and the agents. So here we have an intelligent agent acting upon the world with intelligence, but the part of the world they're acting on with the intelligence is the generativity component of our intelligence definition. So we get a higher level of generativity. It can act upon the world model in different ways. It can act upon the world model more specifically. And then there's a selection action. So if there are a lot of different options that I can act upon the world model with, selection then restricts the states of the world model and makes the whole thing more specific. And you can see the part of the equation that's relevant here. So this actually can be shown in the real world in video game performance, where you can improve someone's expertise by making them play a video game for hours and hours and hours. And it's interesting to note that in real world performance, it isn't linear, and it isn't even log linear. It has these dips and nonlinearities in it that maybe are described by our super performance model. And so we can even extend that further to open looped intelligence augmentation, where feedback from the selective component is more sporadic. And this may actually help shape the world model states even more. So it can open up the loop for adaptation to new situations. So how do we construct good world models and achieve strong intelligence augmentation? And so one of those is appealing to the idea of variety from the Evergood regulator theorem. And in the Evergood regulator theorem, it says that variety can destroy variety. And this is the case where too many states in a world model without a corresponding representation of the intelligent system acts to destroy information. So these anti-aliasing mechanisms actually destroy information provided by the source of the intelligence. And so we can solve this by modifying the amount of expressivity of our generative process of intelligence. So it means that we want to be able to create a number of alternatives or a number of alternate states. And so that process, we can tweak that. And we want to tweak it to match the intelligence's learning rate. So we want to match the performance of both the intelligence and the world model so that it can successfully learn and represent all necessary state information. And finally, the high quality of regulation provides a means for strong AI. So finally, when we have a high quality of regulation, it provides a means for strong intelligence augmentation. So what is the quality of regulation? What is the quality of this regulation between the intelligence and the world model? Is it good enough to enable this sort of augmentation through feedback or through open-ended means? We want to enable the conditions for maintaining information acquisition via feedback. And so there's this example in the paper of a human learner using a dictionary. The human learner is the intelligence, and the dictionary is the world model. The human learner often does not know all the linguistic states or words available in the dictionary. If the learner acquires too few words, the dictionary is not a suitable intelligence augmentation tool, and instead requires a more detailed curriculum for an instruction, and this is where we get this augmentation process. The dictionary that is missing too many linguistic states will hamper the learner's ability to augment their intelligence, and a learner using a dictionary as a lookup function supports the well-regulated acquisition of a larger vocabulary. Thanks for your attention.
Well, thank you, Bradley. Does anyone have questions? Okay.
Hi, congratulations for the presentation. I would like to understand, there is a slide where you show that there is like this difference that you assess between the world model and the real world. is from what I understood. Maybe I didn't get it so well, but you are using like channel entropy to try to assess the difference between the entropies between the two environments.
Yeah.
I would like to understand why you use like the difference. Wouldn't it be better to use, for example, mutual information, or maybe if you're trying to assess the information that of the encoding, maybe you can use like conditional channel entropy. So.
Oh, you could. I just used that as the example. I mean, the idea is that there's this mismatch between the two, and that's kind of where that comes from. But you could do that in other ways, and you could certainly get different types of relationships between the two.
Okay, thank you.
Someone else? No? Okay.
Much, Bradley. Congratulations.
Thank you.
Well, people, we are about to conclude today's session, so let's follow with the last presentation that will be performed by Viviana Dueñas.
Hello, everybody. My name is Viviana Dueñas. I will present my research called Biologically Inspired Computational Models of Visospatial Working Memory, a systematic review. I am from University of Guadalajara. House contents, we include introduction, methodology, research questions, challenges, and conclusions. In the recent decades, artificial intelligence has advanced rapidly, which is forced to develop systems that mimic human cognition. One approach involves biologically inspired models based on humans, insects, rodents, or primates. These cognitive architectures are composed of cognitive functions, as perception, attention, planning, decision making, learning, memory, among others. One cognitive function is the visospatial working memory. It is fundamental cognitive component of the entity that allows them to explore their visual environment. This kind of memory is made up of visual working memory and spatial working memory. The visual working memory is an entity limited capacity for active visual representation. It allows the maintenance of relevant visual information available for subsequent behavior. The spatial working memory is an entity limited capacity for active representation or the collection of relevant objects. Visual working memory enables us to retain information about attributes such as color, shape, and textures, whereas spatial working memory facilitates the recalls of the location and arrangement of objects. Some application of this memory is the spatial navigation, planning, decision making, or interaction with the environment. Somebody applications, sorry, boot are many, both spatial memory, working memory, and visual memory are used with humans and animals. In humans, spatial working memory helps them navigate from one place to other. With visual memory, aids in recognizing landmarks and remembering visual details. In animals, these types of memory are essential for finding food, recognizing their environment, and stay safe from predators. We are formulate 6 research questions. The first, what bio-spirit approach have been used to develop computational models of visuospatial working memory? Second, what cognitive function have considered for developing for these models? What brain areas have been considered? What algorithmic approach have you used? What computational strategies have been used? What challenges exist in the design of these models? We use for the systematic review the methodology Prisma. We searched in database how Scopus, IEEE, ACM, Engineering Village, PubMed, using these keywords. And we considered 9 additional sources. We obtained a total 4,072 results. After removing duplicates, we obtained 3,290 results. After checking title and answer, we obtained 186 for eligibly based on full articles. We obtained 29 articles, and it's the result final. For the first question of investigation, we found 4 types of approach. Neuroscience, the most common, using real data, psychology, based on how people behave, neuropsychology, which represents a blend of psychology and neuroscience, pardon. And phylogenetic, ontogenetic, looking at how memory evolved or grows over time. For the second question, we found 7 areas. What these models include: visual working memory, spatial working memory. In the case of visual working memory, recognize the environment, make decision or navigate. Spatial working memory, make the mental representation of space and the location of objects. Long-term memory, to save past experience, decision making, especially for navigation tasks. Visual perception, to process what the system has. However, visual attention, which helps focus on important things is not used often. On the brain areas identified. The hippocampus is the most common, which is important for spatial memory. Some models also simulate place cells, which helps activate distance and position. Head direction will show where the head is pointing. Other areas like prefrontal cortex and temporal cortex also appear. We look at the algorithms used. The most popular are neural networks, graphs directed, that shows how different elements compete. Estimation algorithms are based on statics. Gaussian algorithms are based in Gauss theory. We also observed that these algorithms adopt distinct spatial approach, while we categorize it based on their frame or reference. Egocentrics presents spatial information relative to the subject's proper position or perspective. Allocentric represents the environment independently of the subject position, often using a math-like object and centered representation. Hybrid, what is a combination of egocentric and allocentric. We saw models are tested in controlled real environments like labs or maze, to 3D virtual environments which simulate real space. Some used simple 2D virtual worlds. For test models in controlled real place, Buddhist header because not easy to control all variables. We also found many challenges. The first, the brain is more complex. Most models focus on only one task, like navigation, and not the full range of mental abilities. It's still hard to connect all mental systems. Dealing with complex, messy information, like what we get from the sensor, is still very difficult. In conclusion, neuroscientific evidence has become increasingly relevant in recent decades, has a foundation for developing these models. Other complementary approaches have also been used, included neuropsychological, phylogenetic, and ontogenetic perspectives. The most commonly integrated, additionally, cognitive function in visuospatial working memory models were identified. The most commonly used algorithmic approaches for implementing these view-inspired models were classified. The most common testing strategies and environments were described, concluded that controlled environments are currently the most frequently used. This is because real work environments with high variability still pose a significant challenge for current models. are your feelings? Thank you for your attention.
Thank you, Viviana. Do we have any questions? No? Okay.
Thank you very much. I think this is good work. It's needed. One question I have about just overall methodology, you're looking at those 29 papers, and each one of those papers, it's hard to say whether they represent a part of a larger research program, meaning that you might have a paper that is focused on one aspect of visuospatial working memory, and then another paper from that same research program that's focused on a different aspect. So would it change any of your conclusions about sort of limited functionality being modeled if you looked across papers, if those papers were sort of building on the same system, if that makes sense? So if you were to cluster based upon, say, cognitive architectures, would you see maybe that some of those papers represent specific work on a larger system where it might accumulate, or are all of these things, do you think, really completely distinct? If that makes sense? Yeah, I could try to rephrase if, so do any of the papers represent work on the same system? Like where two of the papers might be on one system, or is there, everyone is a distinct system? If that makes sense.
Are you referring to cognitive function?
Yes, so like if you had multiple papers for the same cognitive architecture, for example, where if you combined those two together, you might have a different conclusion about what's covered in totality, if that makes sense.
Only for the visuospatial working memory is the cognitive function.
Sorry, I couldn't quite hear. Could you say one more time, please?
Only is visuospatial working memory, the cognitive function.
Thank you.
Okay.
Well, my question is more a curiosity. Why didn't you use Google Scholar in your research?
But not is a scientific database. And it's only general papers, not specific of database.
Because Google Scholar has a lot of papers, so this could be an interesting thing to search.
Google Scholar is a collection of all papers, not specific a database. It's for this.
Okay, thank you.
Thank you, Doctor. Well, good job, Viviana, and thank you for your presentation. Someone else? Okay.
Okay, dear attendees, with this presentation, we conclude today's session. So remember, we expect to see you again at 9 a.m. Mexico City time with the same virtual room. Thank you so much and have a nice day.